Our universe is filled with countless stars, galaxies, and unknown objects. From the crushing gravity of black holes to the whisper-light particles that make up dark matter, the universe is stranger and more exciting than we ever imagined. Join us as we explore the most mind-bending discoveries and baffling questions in modern astronomy. We'll journey to the edge of the known universe and peer into mysteries that could lie beyond. NASA's Juno mission has unveiled a fascinating, intricate tapestry of Jupiter's atmosphere that has taken scientists by surprise. One of the most startling discoveries is the presence of massive Earth-sized cyclones clustered around the poles. Unlike any storm systems seen on Earth, these cyclones form geometric patterns with striking regularity. At the North Pole, 8 cyclones form an octagonal pattern, while the South Pole boasts a pentagonal arrangement with 5 cyclones. Remarkably, these storms remain stable over long periods, resisting merger or dissipation, which challenges existing meteorological models. Another intriguing aspect revealed by Juno is the uneven distribution of ammonia within Jupiter's atmosphere. Ammonia appears highly concentrated at the equator, forming what scientists have termed an ammonia-rich equatorial plume. This discovery hints at complex, deep atmospheric processes, possibly involving a form of upwelling that brings ammonia from the planet's depths to its upper atmosphere. Moreover, Juno's data indicates that these atmospheric phenomena extend much deeper than previously thought, stretching down hundreds of miles beneath the cloud tops. This depth provides new insights into Jupiter's internal dynamics, challenging prior assumptions about the gas giant's atmospheric composition and behavior. The New Horizons flyby of Pluto dramatically transformed our understanding of this distant dwarf planet, painting a picture far more complex and dynamic than anyone had anticipated. One of the most striking revelations was the surface diversity, highlighted by vast icy plains, deep canyons, and towering mountains made of water ice. Perhaps the most iconic feature unveiled by New Horizons is the heart-shaped region named Tombaugh Regio, composed of a nitrogen ice plain known as Sputnik Planitia. This region exhibits signs of glacial activity, indicating that Pluto is geologically active, with processes that continuously reshape its surface. Additionally, the flyby revealed an unexpectedly thin but layered atmosphere, composed mainly of nitrogen, with traces of methane and carbon monoxide. These layers extend much higher than predicted, creating a hazy, stratified visual effect as sunlight interacts with atmospheric particles. The atmosphere also shows significant seasonal changes, implying active climatic processes. Furthermore, New Horizons detected small, localized geysers or ice volcanoes, suggesting recent or ongoing internal heat sources that drive surface renewal. These findings collectively shatter the long-standing perception of Pluto as a static, frozen world, instead presenting it as a vibrant, evolving entity with a fascinating and intricate landscape. Scientific evidence pointing to a subsurface ocean beneath Europa's icy crust is compelling and multifaceted. One of the primary indicators comes from observations made by the Galileo spacecraft, which detected a magnetic field around Europa. This magnetic field could be induced by an electrically conductive layer beneath the surface, most plausibly a salty liquid water ocean. Supporting this theory, gravity measurements reveal inconsistencies in Europa's density and mass distribution, suggesting a thick water-based layer beneath the ice. Additionally, surface geology offers visual clues to this hidden ocean. High-resolution images show chaotic terrain with disrupted ice, resembling broken ice flows seen on Earth's polar seas. These formations imply that the icy crust is floating on a liquid layer, as the disrupted patterns match what we would expect if the surface ice were decoupled from the underlying material. Moreover, Europa's surface is crisscrossed with dark, linear features known as lineae, believed to be fractures filled with material from the subsurface. These fractures may form as the icy shell flexes and stretches, driven by gravitational interactions with Jupiter and its other moons, creating conditions that could facilitate the upwelling of subsurface water. Adding to the evidence, recent observations from the Hubble Space Telescope have detected plumes of water vapor erupting from Europa's surface, akin to geysers on Earth. These plumes provide strong, direct evidence of liquid water interacting with the surface. All these lines of evidence combine to paint a compelling picture of an oceanic world hidden beneath Europa's frozen exterior, holding the tantalizing possibility of an environment where life might exist. The mysterious hexagonal storm pattern at Saturn's North Pole is one of the most bizarre and intriguing phenomena observed in our solar system. Discovered by the Voyager spacecraft in the early 1980s and observed in greater detail by the Cassini mission, this geometric wonder defies easy explanation. The hexagon is a massive cloud pattern spanning roughly 20,000 miles across, with each side measuring about 9,000 miles, wider than Earth's diameter. The structure is remarkably stable, having persisted for decades, and rotates with a period of about 10 hours and 39 minutes, synchronized with Saturn's internal rotation. Scientists believe that the hexagon might be formed by atmospheric jet streams and fluid dynamics unique to Saturn's gaseous environment. One prevailing theory is that this shape is a standing wave pattern, an effect that can occur in rotating fluids. Laboratory experiments have demonstrated that when a circular tank of liquid is rotated at different speeds, it can produce polygonal patterns, mimicking what we see on Saturn, but on a much smaller scale. The hexagonal integrity could be maintained by differences in wind speeds, creating a boundary where vortexes can align neatly into a polygonal shape. Adding to the enigma, deep within the hexagon lies a powerful rotating storm, similar to a terrestrial hurricane but stationary and far more ferocious. This storm's eye is clearly defined, surrounded by high-speed winds reaching up to 300 miles per hour. These findings continue to challenge our understanding of planetary weather systems, suggesting that Saturn's atmospheric dynamics operate on principles both familiar and alien, coaxing hexagons out of the natural chaos within a planet's gaseous envelope. The discovery of liquid water on Mars has fundamentally reshaped the search for extraterrestrial life, reigniting interest and enthusiasm among scientists and the public alike. In 2015, NASA announced that recurring slope lineae, dark streaks observed on Martian slopes, were formed by seasonal flows of briny liquid water. This crucial finding was made possible through data from the Mars Reconnaissance Orbiter, which detected hydrated salts, chemical fingerprints of water, within these streaks. The presence of liquid water, even if it is extremely salty, opens up the possibility that microbial life could exist on Mars today, as water is a fundamental prerequisite for life as we know it. This discovery has shifted the focus of Martian exploration missions, directing efforts toward areas where liquid water or subsurface ice might be accessible. Rovers like Curiosity and Perseverance are now tasked with searching for biosignatures, chemical signs that could indicate past or present microbial life. These explorations include drilling into Martian rock and soil, analyzing samples for organic molecules, and even preparing for future missions that might return Martian samples to Earth for detailed study. Identifying regions with liquid water also aids in selecting potential landing sites for human missions, as water is essential not only for sustaining astronauts, but also for producing fuel and oxygen. Furthermore, the discovery of water stretches beyond the immediate implications for life. It informs our understanding of Mars's climatic history and geological processes, as well as the planet's potential to be habitable in its ancient past. This has spurred an expanded interest in comparative planetology, studying Mars to uncover parallels and differences with Earth's own history. The detection of liquid water has thus reinvigorated the quest to answer one of humanity's most profound questions. Are we alone in the universe? By providing a more promising environment for life, Mars has once again become a focal point for astrobiological research. The discovery of unexpected geological activity on Mercury has significantly altered our perception of this small, sun-scorched planet. Prior to recent missions, scientists assumed that Mercury, long considered a geologically dead world, had cooled and contracted sufficiently to cease any major geological changes. However, the Messenger spacecraft, which orbited Mercury from 2011 to 2015, revealed a dynamic landscape that continues to reshape our understanding of the planet's geology. One of the most surprising findings was the presence of relatively young fault scarps, cliff-like landforms that are indicative of tectonic activity. These scarps are the result of the planet's surface contracting as its interior cools, causing the crust to buckle and break. Even more unexpected, evidence suggests that this tectonic activity is not confined to Mercury's distant past, but has been occurring relatively recently, possibly within the last few million years. This indicates that Mercury is still geologically active, a startling revelation for a planet that was presumed inert. These small-scale thrust faults are only a few kilometers long and a few hundred meters high, yet their fresh appearance implies that Mercury's core is continuing to cool and shrink, driving ongoing surface deformations. The young age of these features suggests that Mercury's geological engine has not entirely stopped functioning, which challenges pre-existing models of planetary cooling and tectonics. Another intriguing discovery was made in the form of hollows, which are irregular, rimless depressions scattered across many of Mercury's craters and open plains. These bright, reflective features appear to be relatively young and may form through the sublimation of volatile substances exposed by meteor impacts, a process where solid materials transition directly into a gas. This is particularly fascinating because it implies the presence of volatile compounds beneath Mercury's surface, a surprising find given the planet's proximity to the Sun and its extreme temperatures. The ongoing formation of hollows further emphasizes that Mercury, far from being a static, desolate world, is characterized by continuous and complex geological processes. Uranus's tilted magnetic field and unusual rotation offer intriguing insights into the planet's formation and the dynamic processes that have shaped its evolution. Unlike most planets in our solar system, which have their magnetic fields more or less aligned with their rotation axes, Uranus's magnetic field is significantly tilted from its rotational axis by about 59 degrees. Moreover, this magnetic field is off-center, displaced from the planet's core by roughly 1/3 of Uranus's radius. These anomalies suggest a complex internal composition and structure, differing markedly from what we observe on Earth and other planets. The peculiar characteristics of Uranus's magnetosphere likely stem from its formation and subsequent evolutionary history. A leading hypothesis is that Uranus experienced a catastrophic collision with a massive object, possibly a protoplanet, early in its history. Such an impact could have knocked the planet onto its side, causing its extreme axial tilt of about 98 degrees. This tilt results in an unusual rotation, with Uranus spinning on its side as it orbits the Sun. The collision theory also explains the off-center magnetic field, as the internal dynamo generating the magnetic field might be located in a fractured or uneven layer of the planet's icy and rocky interior. Further supporting this idea, the collision could have stirred Uranus's interior sufficiently to create a complex, multi-layered composition within its mantle and core regions. This could have led to the development of separate dynamo actions within these layers, thereby producing the tilted and offset magnetic field. Additionally, the giant impact would have caused significant mixing of materials, possibly giving rise to unexpected compositions and physical states within the planet. Consequently, Uranus's magnetic peculiarities provide a window into not only the violent events of its past, but also the ongoing processes affecting its interior dynamics and structure. The Cassini mission's grand finale, its dramatic final dive into Saturn, yielded an unprecedented wealth of data, offering new insights into the gas giant's mysterious interior, ring composition, and atmospheric dynamics. As Cassini made its final orbits, it ventured into the previously unexplored gap between Saturn and its innermost rings, a region about 1,200 miles wide. This daring maneuver allowed the spacecraft to gather high-resolution measurements and observations that were impossible from any other vantage point. One of the most significant revelations came from detailed observations of Saturn's gravity field. By precisely measuring the gravitational pull exerted on the spacecraft, scientists were able to probe Saturn's inner structure. The data indicated that the planet's core is larger and more diffuse than previously thought, encompassing a mixture of rock, ice, and metallic hydrogen spanning up to 20,000 miles in diameter. These findings challenge earlier models of Saturn's internal composition, suggesting that the core is not as compact or well-defined as once believed. Additionally, Cassini's close pass between the planet and its rings provided critical insights into the ring's mass and structure. The spacecraft's observations revealed that the rings are surprisingly lightweight, indicating they might be relatively young in astronomical terms, perhaps only about 100 million years old. Moreover, the ring's material is gradually falling into Saturn, a process known as ring rain, driven by the planet's magnetic field. This discovery suggests that the rings might eventually dissipate, reshaping our understanding of their lifespan and dynamics. The mission also delivered invaluable data on Saturn's upper atmosphere. As Cassini descended into the planet, it sampled the atmosphere directly, measuring its composition and temperature while enduring extreme conditions. The spacecraft detected complex organic molecules raining down from the rings into the atmosphere, enriching it with material that could impact atmospheric chemistry. These final observations of atmospheric composition and ring interaction provide a more comprehensive picture of the processes that govern both Saturn and its iconic rings, closing the mission with a legacy of transformative scientific insights. The Great Red Spot on Jupiter, an immense storm larger than Earth itself, is one of the most iconic and enduring features in our solar system. First observed over 3 centuries ago, this colossal anticyclone has been a subject of intense scientific study and fascination. The storm is characterized by its reddish hue, which is likely due to complex chemical reactions between the atmospheric compounds and ultraviolet radiation from the sun. Measuring about 12,000 miles in width and 25,000 miles in length at its peak, the Great Red Spot has often been referred to as a galactic hurricane, with wind speeds reaching up to 400 kilometers per hour. However, recent observations indicate that the Great Red Spot is undergoing significant changes. Data from telescopes and spacecraft like the Hubble Space Telescope and the Juno mission reveal that the storm has been gradually shrinking. Over the past several decades, it has decreased in size by more than half, and its shape has evolved from an elongated oval to a more circular form. This reduction is so pronounced that it now measures about just 10,000 miles across. Additionally, the colors within the spot have varied, sometimes appearing more vividly red and at other times more muted. Each of these changes hints at underlying atmospheric dynamics and shifts in chemical compositions. Scientists are still debating the reasons behind the Great Red Spot's changes. One hypothesis suggests that interactions with smaller surrounding vortices are siphoning off the storm's energy, leading to its gradual diminishment. Another possibility is that alterations in Jupiter's overall atmospheric conditions are influencing the storm's dynamics. While the exact future of the Great Red Spot remains uncertain, its ongoing evolution provides a unique opportunity to study the mechanisms driving Jupiter's chaotic atmosphere, enriching our understanding of planetary weather systems both within and beyond our solar system. The intriguing possibility of a 9th planet lurking in the distant reaches of our solar system has captivated astronomers in recent years, fueled by compelling indirect evidence. This hypothetical planet, often referred to as Planet 9, is thought to reside far beyond the orbit of Neptune, in the region known as the Kuiper Belt. The first hint of its existence came from the peculiar orbital behavior of certain trans-Neptunian objects, particularly a group of these icy bodies with highly elliptical and aligned orbits. These clustering patterns are unusual and suggest the gravitational influence of an unseen massive object. The leading proponents of the Planet 9 hypothesis, astronomers Konstantin Batygin and Mike Brown, proposed in 2016 that a planet roughly 10 times the mass of Earth could explain these anomalous orbits. Their calculations indicate that this massive planet would orbit the Sun at an average distance of around 400 to 800 astronomical units. 1 astronomical unit is the distance between Earth and the Sun, taking between 10,000 to 20,000 Earth years to complete a single orbit. Such a distant and sizable planet would exert sufficient gravitational force to shepherd the TNOs into their observed configurations, acting as a cosmic shepherd guiding their paths. Further supporting evidence comes from computer simulations that test the stability of the outer solar system with and without the presence of Planet 9. These simulations show that including a 9th planet results in a more accurate representation of the current arrangement and motion of trans-Neptunian objects. Additionally, some researchers point to irregularities in the orbits of known planets and dwarf planets, suggesting that the gravitational influence of a distant large object could account for these discrepancies. While no direct observation of Planet 9 has been made, various astronomical surveys and telescopes are actively hunting for this elusive world. Its detection would not only confirm a long-suspected member of our solar system, but also enhance our understanding of planetary formation and the dynamic processes governing the outer regions of our cosmic neighborhood. The search for Planet 9 remains one of the most tantalizing quests in contemporary astronomy, offering the promise of a significant discovery in our own celestial backyard. Hot Jupiters are a class of exoplanets that bear striking similarities to Jupiter in terms of mass and size, but defy conventional expectations by orbiting extremely close to their host stars. These planets are located so near their stars that their orbital periods are usually less than 10 days, causing them to experience intense stellar radiation and heat. As a result, surface temperatures on hot Jupiters can soar to thousands of degrees Celsius, making these worlds blisteringly hot. The existence of hot Jupiters challenges traditional theories of planetary formation, which are largely based on our understanding of our own solar system. According to the widely accepted core accretion model, gas giants like Jupiter should form beyond the snow line, the region in a young star system where temperatures are low enough for volatile compounds like water to condense into solid ice grains. In such environments, icy grains can rapidly accumulate to form a solid core, which can then gather a substantial envelope of gas. The proximity of hot Jupiters to their stars contradicts this model, as it would be nearly impossible for such massive planets to form in the high-temperature environments close to a star. This discrepancy has led scientists to propose alternate explanations. One leading hypothesis is the concept of planetary migration. It suggests that hot Jupiters originally formed beyond the snow line, like conventional gas giants, but later migrated inward due to gravitational interactions with the protoplanetary disk or other planets. This inward journey could result in a dynamically unstable orbit that stabilizes close to the star. Additionally, tidal forces exerted by the host star could circularize the migrating planet's orbit and lock it into synchronous rotation, where one side permanently faces the star. This results in a phenomenon known as tidal locking, contributing to the extreme temperature variations between the planet's day and night sides. The discovery of hot Jupiters has sparked a re-evaluation of planet formation models and highlighted the dynamic and diverse architectures that planetary systems can assume. Their study continues to deepen our understanding of the myriad ways in which planets can evolve and maintain stable orbits under a wide range of stellar and environmental conditions. The discovery of the TRAPPIST-1 system has had a profound impact on our understanding of habitable worlds and has significantly expanded the scope of where we might look for extraterrestrial life. Announced in 2017, the TRAPPIST-1 system, located about 40 light-years from Earth, comprises 7 Earth-sized planets orbiting a cool, dim M-dwarf star. What makes this discovery particularly remarkable is that 3 of these planets reside in the star's habitable zone, the region where conditions might be just right for liquid water to exist on the surface, which is a key criterion for habitability as we understand it. This system has challenged several preconceived notions about the conditions necessary for habitability. One of the major revelations is that potentially habitable worlds can exist around M-dwarf stars, which are the most common type of star in our galaxy. Unlike our Sun, M-dwarfs are smaller, cooler, and emit most of their radiation in the infrared spectrum. This means planets need to orbit very close to these stars to be in the habitable zone. In the case of TRAPPIST-1, all 7 planets orbit closer to their star than Mercury does to the Sun. Despite these tight orbits, the planets are not necessarily hostile. The TRAPPIST-1 star's lower luminosity and cooler temperatures create a compelling case for the potential of life in these tight-knit systems. The discovery has also emphasized the idea that habitable worlds might be much more common than previously thought. The sheer number of potentially life-supporting planets in just one system suggests that there could be many more such systems throughout the Milky Way. This realization energizes the search for life beyond Earth and prioritizes the study of M-dwarf systems in exoplanet research. Moreover, the close proximity and transit alignment of the TRAPPIST-1 planets make them ideal candidates for atmosphere characterization with current and upcoming telescopes, such as the James Webb Space Telescope. Detailed atmospheric studies can reveal the presence of gases that might indicate biological activity, such as oxygen and methane, further aiding the search for extraterrestrial life. The TRAPPIST-1 system has revolutionized our understanding of where habitable worlds might be found, suggesting that environments suitable for life might be much more widespread than previously believed. It underscores the significance of M-dwarf stars as potential hosts for life, prompting a reorientation of observational strategies and sparking renewed excitement in the quest to find life beyond our solar system. A super-Earth is a type of exoplanet that has a mass larger than Earth's, but significantly less than that of the gas giants like Uranus and Neptune. Typically, these planets have masses up to about 10 times that of Earth. Super-Earths can be rocky, like our planet, or they may also possess thick atmospheres depending on their mass and proximity to their host star. Their composition likely ranges from terrestrial-like structures with significant quantities of rock and metal to ocean worlds or planets with extensive gas envelopes. The discovery of super-Earths has expanded our understanding of planetary formation and the diversity of planetary systems in the galaxy. They are particularly intriguing because their size places them in a range where they could potentially have Earth-like conditions, including the possibility of liquid water and habitable environments. However, their exact characteristics can vary widely. Some may have atmospheres that are too thick to support life as we know it, while others might be more habitable. Observations have shown that super-Earths are extremely common in our galaxy. Indeed, studies using data from the Kepler Space Telescope and other observational programs have revealed that they are among the most prevalent types of exoplanets. Estimates suggest that around 30% or more of Sun-like stars could host at least one super-Earth in their habitable zones, where conditions might be right for liquid water to exist. The high frequency of super-Earths raises fascinating questions about the likelihood of life beyond our solar system. It also challenges our current theories of planetary formation, which were initially based on our solar system's architecture, where no super-Earth exists. The fact that these planets are so common suggests that the processes that lead to their formation might be more accessible or robust than those that create Earth-sized planets like our own. In sum, super-Earths represent a vital component of the exoplanetary landscape, offering a middle ground between terrestrial planets and gas giants. Their prevalence in our galaxy not only makes them compelling targets for the search for extraterrestrial life, but also drives ongoing efforts to understand the complex processes that govern planet formation and evolution. Astronomers employ a variety of sophisticated methods to detect exoplanets, each with its unique advantages and challenges. These techniques have revolutionized our understanding of the universe, revealing thousands of worlds beyond our solar system. The most prominent methods include the transit method, the radial velocity method, direct imaging, astrometry, and gravitational microlensing. The transit method has been extraordinarily successful, particularly with space telescopes like Kepler and TESS. This method involves monitoring the brightness of a star over time. When an exoplanet crosses in front of its host star, it causes a slight temporary dimming of the star's light. By measuring these periodic dimming events, astronomers can infer the presence of a planet, estimate its size, and determine its orbital period. This method is particularly effective for identifying planets that orbit relatively close to their stars. The radial velocity method, also known as the Doppler spectroscopy method, detects exoplanets by measuring the star's motion toward or away from us. As a planet orbits a star, its gravitational pull causes the star to wobble slightly. This wobble affects the light spectrum of the star, causing periodic shifts toward red and blue wavelengths as the star moves away from and toward us, respectively. By analyzing these shifts, astronomers can infer the presence of a planet, its mass, and its orbital characteristics. This method is especially useful for detecting larger planets that exert a significant gravitational influence on their stars. Direct imaging is a more challenging and less common method, primarily due to the difficulty of distinguishing the faint light of an exoplanet from the overwhelming brightness of its host star. Nevertheless, advancements in technology such as adaptive optics and coronagraphs have enabled astronomers to capture images of exoplanets directly. Direct imaging is particularly valuable for studying the atmospheres and surface conditions of exoplanets, as it allows for the acquisition of detailed spectra. Astrometry involves precisely measuring the positions of stars in the sky and detecting tiny changes in their positions due to the gravitational pull of orbiting planets. This method requires exceptional precision and is less commonly used, but it can be effective for detecting larger planets at greater distances from their stars. Gravitational microlensing takes advantage of the gravitational field of a star to magnify the light of a background star when it passes in front. If the foreground star has a planet, the planet's gravitational field can create a distinctive signature in the light curve, indicating its presence. This method is particularly useful for finding planets at more considerable distances from their stars, and even for detecting rogue planets that do not orbit any star. Each of these methods contributes valuable information about exoplanets, and when used in combination, they provide a more comprehensive understanding of planetary systems beyond our own. Together, they have illuminated the incredible diversity of exoplanets, from hot Jupiters to rocky super-Earths, expanding our knowledge of the universe and the potential for life beyond Earth. The Goldilocks zone, also known as the habitable zone, is a region around a star where conditions may be just right, neither too hot nor too cold, for liquid water to exist on the surface of a planet. This concept borrows from the Goldilocks tale, indicating that the environment within this zone is just right for sustaining life as we know it. Scientists emphasize the importance of liquid water because it is a fundamental ingredient for life on Earth and is believed to be vital for life elsewhere in the universe. Liquid water acts as a solvent, allowing chemical reactions to occur, which are necessary for the development of biological systems. The significance of the Goldilocks zone extends beyond just the presence of water. It also influences the types of atmospheres a planet can maintain. Planets in this zone have better chances of holding on to their atmospheres, which can shield life forms from harmful radiation and contribute to climate stability. For instance, Earth is within the Sun's Goldilocks zone, enabling it to support a diverse range of ecosystems. Finding exoplanets within their stars' habitable zones is a key focus for astrobiologists searching for potential extraterrestrial life, as these planets are the most promising candidates where life-supporting conditions could be present. Thus, the Goldilocks zone is a critical factor in the ongoing quest to determine whether we are alone in the universe. Certain exoplanets orbit their stars in exceptionally short periods, sometimes completing a full revolution in just a few hours, due to their proximity to their host stars. These planets are often classified as ultra-short-period planets, and are drawn so close to their stars that the gravitational forces between the bodies become immense. This tight orbit results in incredibly fast orbital speeds. Such extreme proximity also subjects these exoplanets to intense stellar radiation and tidal forces, leading to unique and harsh environments. The proximity of these planets to their stars means they experience temperatures rising into thousands of degrees Celsius, causing dramatic atmospheric and surface phenomena. For instance, these exoplanets may exhibit synchronized rotation, showing the same face to their star at all times, a state known as tidal locking. This situation results in one side of the planet being perpetually baked by stellar heat, while the opposite side remains in constant darkness and significantly cooler. The intense conditions raise intriguing questions about the types of atmospheres these planets might sustain and whether they could support life in forms radically different from those we are familiar with on Earth. This phenomenon underscores the diversity of planetary systems in the galaxy and challenges our understanding of the potential for life in such extreme environments. Rogue planets are fascinating celestial wanderers that drift through the galaxy without tethering to the gravitational pull of a host star. They have been ejected from their original planetary systems, possibly due to dynamic interactions with other planetary bodies or the gravitational influence of a nearby passing star. Despite this isolation, rogue planets demonstrate remarkable resilience in the interstellar medium, surviving in the cold depths of space through various means. These planets possess internal heat sources that can support them despite the lack of sunlight. For example, many rogue planets retain the residual heat from their formation in their cores, slowly radiating warmth over eons. Additionally, some larger rogue planets may experience geothermal heating, generated by radioactive decay within their interiors, similar to the processes found on Earth. This heat can create subsurface oceans beneath thick ice crusts, where liquid water might exist in a stable state. Such conditions raise intriguing possibilities for life, suggesting that these solitary travelers could harbor microbial ecosystems in deep, habitable environments shielded from the rigors of space. Rogue planets challenge conventional notions of habitability and expand our understanding of where life might thrive in the universe. Binary star systems, where two stars orbit around a common center of mass, introduce complex gravitational dynamics that profoundly influence planetary formation and habitability. Planets in these systems typically fall into two categories based on their orbits: circumbinary planets, which orbit both stars in a wide encompassing path, and circumstellar planets, which orbit just one of the stars, with the second star being a distant companion. The formation of planets in these systems faces significant challenges due to the fluctuating gravitational forces exerted by two stars. This can lead to destabilizing perturbations in the planetary disk, potentially preventing planetesimals from coalescing efficiently. However, if the initial conditions are favorable, planets can still form and thrive. For example, NASA's Kepler mission has identified several circumbinary planets, debunking previous assumptions that such environments were too chaotic for stable planetary formation. Regarding habitability, the twin suns of a binary system can influence a planet's climate and radiation exposure. A stable orbit in the habitable zone, where conditions for liquid water are met, must be maintained despite the gravitational tug-of-war. Circumbinary planets might experience more varied climate patterns due to the shifting positions of their twin suns, potentially resulting in complex seasonal changes. On the other hand, a circumstellar planet might face periodic gravitational disturbances from the secondary star, affecting its orbit and consequently its climate stability. Despite these challenges, the discovery of planets in binary systems broadens the scope of potential habitable worlds, illustrating the incredible adaptability of planetary systems in the galaxy. A lava world is an exoplanet characterized by extreme surface conditions, where vast regions are covered with molten rock. Such planets typically orbit very close to their host stars, enduring intense heat that keeps their surfaces in a perpetually molten state. One of the most noted examples of a lava world is the exoplanet 55 Cancri E, which orbits its star so closely that temperatures can soar above 2,000 degrees Celsius, melting rock into a searing lava landscape. Studying lava worlds provides crucial insights into planetary evolution, particularly regarding the thermal and geological processes at play. These planets offer natural laboratories for understanding the early stages of planetary development, resembling the molten conditions that Earth likely experienced shortly after its formation. Observations of lava worlds can shed light on processes such as planetary differentiation, where heavier materials sink to form a core and lighter materials create a crust. Moreover, the intense heat and volcanic activity on these worlds enable scientists to study outgassing processes, where volatile compounds are released from a planet's interior to the atmosphere, an essential aspect of atmosphere formation and evolution. Additionally, the extreme environments of lava worlds help to refine theoretical models of planet-star interactions, especially concerning tidal locking and planetary deformation under strong gravitational forces. By examining these fiery exoplanets, scientists can better grasp the range of planetary conditions across the universe, leading to a deeper understanding of the factors influencing planet formation, stability, and potential habitability. Some exoplanets defy our traditional understanding of atmospheric composition by exhibiting features and elements that are unexpected or unlike anything observed within our own solar system. These peculiarities challenge existing models of planetary formation and atmospheric science, prompting researchers to rethink the chemical and physical processes that govern such environments. One striking example is the exoplanet WASP-33b, a type of gas giant known as a hot Jupiter. It orbits so close to its host star that its atmospheric temperatures can reach up to 3,000 degrees Celsius. At such extreme temperatures, the atmosphere contains exotic elements like titanium oxide, a molecule more commonly associated with stellar rather than planetary atmospheres. This discovery not only highlights the intense thermal dynamics of hot Jupiters, but also suggests the presence of strong thermal inversion layers, where temperature increases with altitude instead of decreasing. Another intriguing case is the exoplanet HD 189733b, which confounds scientists with its deep blue hue. Unlike Earth, whose blue color comes from oceans and atmospheric scattering, HD 189733b's color is attributed to a hazy atmosphere filled with high-altitude clouds of silicate particles. These particles are believed to form a type of exotic weather system where glassy rain falls sideways due to ferocious winds blowing at speeds of up to 5,000 miles per hour. Such enigmatic atmospheric compositions necessitate more complex and nuanced models of planet formation and evolution. They also underscore the diversity of environmental conditions that can exist, potentially leading to novel chemical pathways and processes. By studying these extraordinary atmospheres, scientists are not only expanding our understanding of what is possible in planetary science, but also refining the criteria for habitability and the potential for diverse forms of life. The first image of a black hole, unveiled in April 2019, was captured using an innovative and unprecedented approach called Very Long Baseline Interferometry. This technique involved an international collaboration under the Event Horizon Telescope project, which linked together 8 ground-based radio telescopes located across the planet. By synchronizing these telescopes to observe the same region of space simultaneously and combining their data, scientists effectively created a virtual Earth-sized telescope capable of achieving the high resolution necessary to capture the black hole. The black hole imaged is located at the center of the galaxy M87, approximately 53 million light-years away from Earth. The EHT targeted this supermassive black hole known as M87 star, aiming to capture its event horizon, the boundary beyond which nothing, not even light, can escape its gravitational grip. Achieving this involved meticulously coordinating the telescopes, which are spread across continents, including sites in Hawaii, Chile, Spain, and the Antarctic, and required exceptionally precise atomic clocks to ensure synchronization down to the microsecond. To assemble the final image, the EHT team gathered petabytes of data over multiple nights and employed advanced algorithms to process and interpret the colossal datasets. The resulting image revealed a bright ring-like structure with a dark central region, consistent with theoretical predictions of a black hole's shadow. This iconic depiction not only provided visual confirmation of black holes' existence, but also offered a valuable opportunity to test and refine Einstein's general theory of relativity under extreme conditions. The successful capture of this image marks a monumental achievement in astrophysics, showcasing the power of global collaboration and technological innovation in expanding our understanding of the universe. The event horizon of a black hole is a fascinating and mysterious boundary marking the point of no return. At this boundary, the gravitational pull becomes so overwhelming that not even light can escape its grasp. This makes the event horizon essentially an invisible surface. Anything that crosses it disappears from the observable universe. The concept of the event horizon is rooted in the theory of general relativity, which describes how objects with substantial mass warp the fabric of space-time. One key aspect of the event horizon is that it represents a threshold beyond which conventional physics ceases to be adequate. As an object approaches the event horizon, it experiences extreme gravitational forces that create extraordinary effects. For instance, from an external observer's perspective, time appears to slow down drastically for the object nearing the event horizon due to intense gravitational time dilation. To the observer, the object never seems to quite reach the event horizon. Instead, it appears to freeze and gradually fade away as its light becomes increasingly redshifted. For the object itself, however, the experience is markedly different. Upon crossing the event horizon, it would continue its descent into the black hole without noticing any sudden changes at the exact crossing point, according to classical general relativity. However, as it ventures further, it would be subjected to stronger tidal forces that could eventually spaghettify or stretch it lengthwise while compressing it sideways, due to the black hole's immense gravitational gradient. Inside the event horizon lies the singularity, where the curvature of space-time becomes infinite and the laws of physics, as we currently understand them, break down. This presents one of the most profound puzzles in modern astrophysics, driving ongoing research to unify general relativity with quantum mechanics. The event horizon thus remains a key area of study, illuminating the limits of our understanding and pushing the boundaries of theoretical physics. The formation of supermassive black holes, which reside at the centers of most galaxies, including our Milky Way, is a subject of intense study and fascination in astrophysics. These cosmic giants can have masses millions to billions of times that of our Sun, and their origins are thought to be intricately linked with the evolution of galaxies themselves. One predominant theory suggests that supermassive black holes originate from the collapse of massive gas clouds in the early universe. These primordial clouds, containing vast amounts of hydrogen and helium, could rapidly collapse under their own gravity to form seed black holes with masses between 100 and 1,000 times that of the Sun. Over time, these seed black holes could grow significantly through a process known as accretion. As they attract and consume surrounding gas and dust, they accumulate mass, releasing enormous amounts of energy in the form of radiation, often observed as quasars. Another possible formation mechanism involves the mergers of smaller black holes. In the dense environments of early galaxies, frequent collisions and mergers of stars could lead to the formation of numerous stellar mass black holes. Over billions of years, these smaller black holes could merge to form increasingly larger ones, eventually evolving into supermassive black holes. Galactic mergers, which were more common in the early universe, likely played a critical role in this process, as the central black holes of colliding galaxies would eventually coalesce. The relationship between supermassive black holes and their host galaxies is also crucial. Observations reveal a strong correlation between the mass of a galaxy's central black hole and the mass of its bulge, suggesting a co-evolutionary process. The energy emitted by the accretion of matter onto the black hole can regulate star formation within the galaxy, influencing its growth and evolution. Despite numerous insights, the exact pathways forming these colossal black holes remain an active area of research, with ongoing observations and simulations aiming to unravel this cosmic mystery. Gravitational waves are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Predicted a century ago by Albert Einstein's general theory of relativity, these waves travel at the speed of light, carrying information about their cataclysmic origins as well as the nature of gravity itself. The detection of gravitational waves represents one of the most groundbreaking advances in astrophysics, offering a new way to study celestial phenomena, particularly black holes. Gravitational waves are generated by accelerating massive objects, such as when two black holes spiral into each other and merge. When these waves pass through Earth, they cause minuscule distortions in space-time that can be detected by highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory and Virgo. The first direct detection of gravitational waves, announced in 2016, came from such a merger of two black holes about 1.3 billion light-years away. This observation confirmed not only the existence of gravitational waves, but also provided the first direct evidence of binary black hole systems. Studying gravitational waves opens a unique window into the hidden workings of black holes. Unlike electromagnetic waves, gravitational waves are not easily absorbed or scattered by matter, allowing them to travel across the universe largely undisturbed. This means they can carry pristine information from extreme environments that are otherwise inaccessible. By analyzing the waveform of gravitational waves, scientists can infer the properties of their sources, including the masses, spins, and even the dynamics of the black holes involved. Furthermore, gravitational wave astronomy helps us understand the population and distribution of black holes in the universe. It can reveal the rates of stellar mass black hole mergers, offering insights into the environments where these black holes form and evolve. The data gathered also tests the predictions of general relativity under the most extreme conditions, potentially pointing to new physics if anomalies are found. In this way, gravitational waves not only enrich our understanding of black holes, but also augment our comprehension of fundamental physics. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking in 1974, suggesting that black holes are not entirely black, but can emit radiation due to quantum effects near their event horizons. This groundbreaking idea arises from the interplay between quantum mechanics and general relativity, two pillars of modern physics that typically operate in distinct realms: quantum mechanics at the atomic scale and general relativity at cosmic scales. Hawking radiation is a consequence of the peculiar properties of quantum fields in curved spacetime. Near the event horizon of a black hole, the strong gravitational field is thought to cause pairs of virtual particles, one particle and its antiparticle counterpart, to spontaneously form from the quantum vacuum. Normally, these pairs annihilate each other almost immediately. However, if such a pair forms right at the edge of the event horizon, it is possible for one particle to fall into the black hole while the other escapes into space. To an outside observer, this escaping particle appears as radiation emanating from the black hole. The particle that falls into the black hole effectively has negative energy relative to the outside universe, causing the black hole to lose a tiny amount of mass over time. The concept of Hawking radiation challenges our understanding of black holes in several profound ways. First, it implies that black holes are not eternal. Over incredibly long timescales, they can evaporate completely as they emit Hawking radiation and lose mass. This leads to the intriguing possibility that black holes can ultimately vanish, releasing their energy back into the universe. Moreover, Hawking radiation touches on the puzzling issue of information loss in black holes. According to classical general relativity, all information about the matter that falls into a black hole is lost to the rest of the universe, residing within the event horizon and ultimately disappearing with the black hole's evaporation. However, this notion conflicts with the principles of quantum mechanics, which assert that information must be preserved. This tension between the two theories has sparked significant debate and research, leading to new concepts such as the holographic principle and the idea of black hole complementarity. Hawking radiation thus serves as a tantalizing bridge between quantum mechanics and general relativity, pointing towards the need for a unified theory of quantum gravity that can reconcile these seemingly incompatible domains. Black holes have an astounding ability to distort time and space around them due to their immense gravitational fields, a phenomenon predicted by Einstein's general theory of relativity. The stronger the gravitational field, the more pronounced the distortion, reaching extremes near the event horizon, the boundary beyond which nothing can escape the black hole's pull. Firstly, let's consider the concept of space-time, which combines the three dimensions of space with the dimension of time into a single four-dimensional continuum. A black hole exerts such a strong gravitational force that it warps this continuum to an extreme degree. Imagine space-time as a two-dimensional rubber sheet. Placing a heavy object on this sheet will cause it to stretch and curve around the object. Similarly, a black hole creates deep pits in the fabric of space-time, dramatically bending the paths that light and matter take when passing near it. This warping of space has intriguing observational consequences. Objects near a black hole will follow curved trajectories as they are deflected by the warped space-time, resulting in phenomena like gravitational lensing, where light from background stars or galaxies bends around the black hole, creating multiple or distorted images. The stronger the black hole's gravitational field, the more pronounced this lensing effect becomes, providing astronomers with indirect evidence of black holes. Time, too, experiences significant distortion near a black hole, a phenomenon known as gravitational time dilation. According to relativity, the stronger the gravitational field, the slower time ticks relative to an observer at a distance. Near a black hole, this effect is magnified to an extraordinary extent. For an object approaching the event horizon, time appears to slow down drastically from the perspective of a distant observer. If a person were watching from a safe distance, they would see the object gradually slow and freeze at the boundary, never actually observing it cross into the black hole. However, the object itself would perceive time normally and would cross the event horizon without noticing this extreme time dilation. This distortion of time and space has profound implications for our understanding of the universe. It challenges our perceptions of what is possible within the realms of physics and provides a unique laboratory for testing the predictions of general relativity. These extraordinary effects underline the importance of black holes in the broader context of cosmic evolution and the ongoing quest to understand the fundamental nature of reality. A quasar, short for quasi-stellar object, is one of the most luminous and energetic phenomena in the universe, and it is intrinsically linked to supermassive black holes. These extraordinary objects reside in the centers of galaxies, where they draw in vast amounts of surrounding matter. As this matter falls towards the black hole, it forms an accretion disk, a swirling superheated disk of gas, dust, and other material. The extreme gravitational forces exerted by the black hole accelerate and compress this material, causing it to emit staggering amounts of electromagnetic radiation, particularly in the radio, ultraviolet, and X-ray wavelengths. The immense brightness of quasars is primarily due to the processes occurring in this accretion disk. Friction and collision among the particles within the disk generate immense heat and release energy, which travels outward as intense radiation. Quasars can outshine entire galaxies despite their relatively compact size. Some quasars are so luminous that they can be observed billions of light-years away, providing valuable insights into the early universe. The relationship between quasars and black holes offers a glimpse into the dynamics of galaxy evolution. The central supermassive black hole powers the quasar by consuming the surrounding material at an astonishing rate. This accretion process not only fuels the quasar's brilliant radiation, but also plays a role in regulating star formation within the host galaxy. The energy radiated by the quasar can drive powerful outflows of gas and dust, which may either trigger star formation by compressing nearby clouds or inhibit it by blowing away the raw material needed for star creation. Thus, quasars are pivotal in shaping their galactic environments over cosmic timescales. Moreover, the observation of quasars has been instrumental in enhancing our understanding of supermassive black holes. The first quasar discovered, 3C273, led to the realization that these objects are closely tied to black holes and are not merely distant stars or galaxies. Quasars also serve as beacons that illuminate the structure and composition of the universe, allowing astronomers to study the intergalactic medium and trace large-scale cosmic structures. As such, these astounding objects continue to be a focal point of research, aiding in the exploration of fundamental questions about the nature of matter, energy, and the evolution of the cosmos. Binary black hole systems, comprising two black holes orbiting around a common center of mass, exhibit behaviors that are markedly distinct from solitary black holes. These interactions lead to complex gravitational dynamics and fascinating astrophysical phenomena that provide rich opportunities for observation and study. One of the most striking features of binary black hole systems is the emission of gravitational waves. As the two black holes orbit each other, their immense gravitational fields cause ripples in spacetime that propagate outward at the speed of light. These gravitational waves carry away energy from the system, causing the black holes to gradually lose orbital separation and spiral closer together. The closer they get, the stronger the gravitational wave signals become, eventually culminating in a dramatic merger. The detection of these waves, as achieved by observatories like LIGO and Virgo, provides direct evidence of binary black hole systems and allows scientists to study the properties of black holes, such as their masses and spins, with unprecedented precision. The merger event itself is an extraordinary spectacle involving the fusing of two black holes into a single, more massive black hole. This process releases a tremendous amount of energy in the form of gravitational waves, often more than the combined energy output of all the stars in the observable universe for the brief moment of the merger. These merger events also provide crucial tests for general relativity, allowing researchers to explore the behavior of gravity in extreme conditions. Before merging, binary black hole systems also exhibit unique dynamical behaviors. The intense gravitational interaction between the pair can lead to phenomena such as orbital precession, where the orientation of the orbit changes over time. This effect is similar to the precession of a spinning top, but it occurs due to the complex interplay of the black hole's masses and spins. The geometry of spacetime around the binary system becomes highly distorted and dynamic, a stark contrast to the relatively static warping found around solitary black holes. Furthermore, the formation and evolution of binary black hole systems also differ significantly from their solitary counterparts. Binary systems can form both from the collapse of massive stellar binaries and through dynamic interactions in dense stellar environments, such as globular clusters. These formation scenarios can influence the characteristics of the black holes, such as their masses, spins, and eccentricities of their orbits. Binary black hole systems offer a dynamic and complex laboratory for understanding gravitational physics, stellar evolution, and the nature of black holes. Their distinctive behaviors, particularly their emission of gravitational waves and their eventual mergers, provide invaluable data that enhances our comprehension of the cosmos. The firewall paradox is a thought-provoking problem in theoretical physics that challenges our understanding of black holes and the principles of quantum mechanics and general relativity. It arises from attempts to reconcile the behavior of black holes with the fundamental tenet of quantum mechanics that information cannot be destroyed. According to general relativity, an observer falling into a large black hole would not experience significant changes as they cross the event horizon due to the principle of equivalence, which states that the laws of physics in a small region of spacetime are the same in a freely falling frame as they would be in the absence of gravity. This means that the event horizon should not be a special or violent place. Instead, it should be smooth and regular. However, from the perspective of quantum mechanics, and in particular Hawking radiation, the story becomes more complicated. Hawking proposed that black holes emit radiation due to quantum effects near the event horizon, leading to the gradual reduction in mass of the black hole over time. This process implies that the black hole can eventually evaporate entirely, raising the question of what happens to the information about everything that fell into the black hole. If the information is lost, it would violate a fundamental tenet of quantum mechanics, which asserts that information must be preserved. To resolve this violation, some theorists suggested that the information might be encoded in the Hawking radiation itself, but this proposal leads to another issue. If there is entanglement between particles just inside and outside the horizon to preserve information, breaking this entanglement would require a significant release of energy, effectively creating a firewall at the event horizon. This firewall would incinerate anything falling into the black hole, contradicting the principle of equivalence that posits a smooth horizon. Thus, the firewall paradox forces a choice between one of three deeply held principles: the smoothness of the event horizon, the preservation of information, or the rules of quantum field theory in curved spacetime. Resolving the paradox would likely require a deeper understanding of how gravity and quantum mechanics coexist, pointing toward a theory of quantum gravity. This ongoing debate underscores fundamental questions about the nature of black holes, the fabric of spacetime, and the ultimate laws of physics that govern our universe. Astronomers and cosmologists have long been puzzled by the existence of intermediate mass black holes, which range from 100 to 100,000 times the mass of our Sun. These black holes create a gap in our understanding of black hole formation, nestled between the well-established categories of stellar mass black holes and supermassive black holes. Stellar mass black holes are known to form from the collapse of massive stars, typically between 10 to 100 solar masses, while supermassive black holes, found at the centers of galaxies, tip the scales at millions to billions of solar masses. The existence of black holes that fall in the intermediate range does not align neatly with either of these known formation processes. One challenge posed by intermediate mass black holes is the ambiguity surrounding their origin. The formation of stellar mass black holes through supernova explosions does not usually yield black holes of such intermediary sizes. Similarly, the mechanisms involved in the births of supermassive black holes, which involve accretion of mass over billions of years, or the merging of multiple smaller black holes in dense star clusters, do not easily explain the presence of these moderately sized entities. Moreover, the difficulty lies in the detection and study of these black holes, as they are neither small enough to be easily seen through X-ray emissions from binary systems, nor large enough to influence their galactic environments as strikingly as their supermassive counterparts. This fascinating middle ground challenges scientists to rethink and broaden their models of black hole growth and evolution, potentially requiring entirely new mechanisms or stages in the life cycles of black holes. The cosmic web is a vast, intricate network of filaments composed primarily of dark matter and gas, and it underpins the large-scale structure of the universe. This web can be visualized as a three-dimensional spiderweb stretching across the cosmos, where the densest knots and threads serve as the scaffolding for galaxies and clusters of galaxies to form. Stretching across billions of light-years, the cosmic web is the grand architecture within which all cosmic structures are embedded. The nodes of this web, where filaments intersect, are especially dense and act as gravitational wells that draw in more matter, leading to the formation of galaxy clusters. The cosmic web significantly influences the universe's overall shape and dynamics. For starters, the distribution of dark matter within the web gravitationally attracts ordinary matter, catalyzing star formation and the development of galaxies in these dense regions. Additionally, the filamentary structures facilitate the flow of gas and galaxies along their paths, contributing to the ongoing growth and evolution of cosmic structures. This continuous movement along the web helps to distribute elements necessary for star and planet formation across different regions of the universe. Therefore, the cosmic web not only forms a map of the universe's vast and varied terrain, but also plays a crucial role in the processes that lead to the complex structures we observe today, ranging from individual galaxies to enormous superclusters of galaxies. Galaxy clusters serve as cosmic laboratories that provide compelling evidence for the existence of dark matter through several key observations. First and foremost, when astronomers measure the velocities of galaxies within a cluster, they find that these galaxies move at such high speeds that the visible matter alone, including stars and gas, cannot account for the gravitational pull necessary to keep them bound together. This discrepancy suggests that there must be an additional invisible form of matter, dark matter, that provides the extra gravitational force needed to stabilize the cluster. Furthermore, gravitational lensing offers another powerful line of evidence. This phenomenon occurs when the massive gravitational field of a galaxy cluster bends and distorts the light from background objects, such as more distant galaxies. By analyzing the degree of this distortion, scientists can map the distribution of mass within the cluster. Remarkably, these mass maps reveal much more mass than what is visible through direct observations of stars and hot gas alone, once again pointing to the presence of dark matter. Another key piece of evidence comes from the study of the temperature and distribution of the hot gas in galaxy clusters as observed through X-ray emissions. This hot gas, which comprises most of the visible mass in a cluster, is held in place by gravity. The temperature of the gas indicates the depth of the gravitational well it resides in. When scientists perform these calculations, they find that the gravitational well is far deeper than can be accounted for by the visible gas and stars alone, implying that dark matter must be providing the additional gravitational pull. Together, these various lines of evidence converge to strongly support the existence of dark matter, which is thought to make up about 85% of the total mass in the universe. Cosmic voids are vast, cavernous regions of space that contain very few galaxies or matter of any kind. These empty expanses can span tens of millions of light-years across and are some of the largest structures in the universe. Despite their emptiness, cosmic voids play a crucial role in our understanding of the large-scale structure of the universe. They are essentially the dark counterpoints to the dense, bright regions of the cosmic web, where galaxies congregate along filaments and clusters. The study of these voids provides valuable insights into the distribution of matter, the properties of dark energy, and the overall evolution of cosmic structures. One of the key revelations from studying cosmic voids is their use in improving our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. By examining the distribution, size, and shape of voids, scientists can gather clues about how dark energy acts over vast distances and over different epochs of the universe's history. The expansion rate of voids, for example, can offer indirect measurements of the universe's expansion rate, offering a complementary method to other observations like supernovae. Moreover, cosmic voids help refine our models of galactic formation and distribution. The properties of voids, such as their scarcity of galaxies and low-density environment, make them excellent laboratories for studying processes that would be impossible to isolate in denser regions. For instance, the absence of significant gravitational interaction in voids allows scientists to observe the impacts of cosmic phenomena like galactic winds and small-scale structure formation without the interfering effects present in more crowded areas. In these vast empty spaces, some of the fundamental forces shaping the universe can be dissected and understood, offering a unique perspective that complements the information gathered from the dense knots and filaments of the cosmic web. The contrasting interplay between cosmic voids and denser regions frames the universe as we see it and helps decipher the underlying principles that govern cosmic evolution. When galaxies collide, they engage in a complex and dramatic dance driven by gravitational forces that can last millions or even billions of years. Unlike typical collisions we might imagine on Earth, galaxy collisions are not characterized by stars and planets smashing directly into each other due to the vast distances between them. Instead, the gravitational interactions between the galaxy's masses, including stars, gas, dust, and dark matter, lead to significant changes in their structures and behaviors. During the initial stages of a collision, the outer regions of the galaxies begin to interact, leading to tidal forces that distort their shapes, often pulling out long streams of stars and gas known as tidal tails. As the galaxies approach each other more closely, their central regions experience intense gravitational interactions, dramatically affecting their morphologies. Spiral arms might be stretched and twisted, while gas clouds within the galaxies can be compressed, leading to bursts of star formation. This phenomenon, known as a starburst, occurs because the compression of gas clouds facilitates new star formation at an accelerated rate. As the collision progresses, the galaxies pass through each other and may separate briefly before their gravitational pull brings them back together for a more significant, often final merger. During this coalescence phase, the supermassive black holes residing at the centers of the colliding galaxies can eventually merge, creating an even larger black hole, releasing immense amounts of energy and sometimes resulting in powerful quasars or active galactic nuclei. The resulting merged galaxy typically settles into a more elliptical shape, lacking the distinct features such as spiral arms, which characterize many of the original colliding galaxies. Over billions of years, these colossal events contribute to the ongoing evolution of galaxies, transforming their structure and star populations. Through these mergers and collisions, galaxies can grow significantly, adding to the complex history etched into the universe's vast cosmic tapestry. Dark energy is an enigmatic force that permeates all of space and appears to be driving the accelerated expansion of the universe. It was first inferred from observations in the late 20th century, when astronomers studying distant supernovae discovered that these exploding stars were dimmer, and hence farther away, than expected. This surprising finding indicated that the universe's expansion rate was not just continuing, but accelerating over time, a revelation that contradicted the long-held assumption that the universe's expansion should be slowing down due to gravitational attraction. Though dark energy remains largely mysterious, it is thought to make up about 70% of the total energy content of the universe. Its effects are most evident on cosmological scales. While gravity works to pull matter together, dark energy exerts a repulsive force, pushing galaxies and other structures away from each other. The exact nature of dark energy is one of the most significant unsolved questions in cosmology. One leading hypothesis is that it could be a property of space itself, connected to the cosmological constant first proposed by Albert Einstein, which implies that the energy density of empty space remains constant over time. The presence of dark energy has profound implications for the fate of the universe. If this repulsive force continues to dominate, the universe will keep expanding at an ever-accelerating rate, leading to a future where galaxies recede from each other faster than the speed of light. This would result in a scenario known as the Big Freeze, where galaxies move beyond each other's observable horizons, stars eventually burn out, and the universe becomes a dark, cold void. Current observations of the cosmic microwave background radiation, the large-scale structure of the universe, and galaxy clusters continue to refine our understanding of dark energy, but its true nature remains one of the most perplexing puzzles in contemporary science. Astronomers map the distribution of dark matter in the universe using several ingenious techniques, with gravitational lensing being one of the most effective. Gravitational lensing occurs when the massive gravitational field of dark matter bends and distorts the light from background objects, like distant galaxies. By carefully analyzing these distortions, scientists can infer the presence and amount of dark matter between the observer and the light source. There are two types of gravitational lensing: strong lensing, which produces dramatic arcs or multiple images of a single object, and weak lensing, which causes subtle statistical distortions in the shapes of many background galaxies. The weak lensing method in particular is powerful for mapping dark matter on large scales, revealing its presence even where no visible matter exists. Another critical method involves observing the motion of galaxies in galaxy clusters. The velocities of galaxies within a cluster can be measured through the Doppler shift of their light. These velocities provide data on the gravitational forces at play, allowing astronomers to estimate the total mass of the cluster, including the unseen dark matter. Interestingly, the observed motion of galaxies within clusters often shows that the visible matter is insufficient to generate the required gravitational pull, leading to the conclusion that a significant amount of dark matter must be present. Cosmic microwave background radiation also offers insights into dark matter distribution. The CMB is the relic radiation from the Big Bang, and its fluctuations in temperature and density offer a snapshot of the early universe. By studying these fluctuations, scientists can model the initial distribution of matter and how it evolved over time, including the influence of dark matter in shaping the large-scale structure of the cosmos. Combining these methods, astronomers create detailed maps of dark matter. These maps show a cosmic web-like structure where dark matter forms a scaffolding within which galaxies and galaxy clusters reside. Advanced technologies and surveys like the Hubble Space Telescope, the Sloan Digital Sky Survey, and future missions like the Euclid Space Telescope and the James Webb Space Telescope will continue to refine our understanding of the dark matter distribution, unveiling more about this invisible yet profoundly influential component of the universe. Galactic filaments are colossal thread-like structures composed primarily of galaxies, gas, and dark matter, forming part of the intricate cosmic web that spans the universe. These filaments can stretch hundreds of millions of light-years and serve as the bridges between galaxy clusters, forming the framework upon which the large-scale structure of the universe is built. Their formation traces back to the early universe following the Big Bang, when initial quantum fluctuations created slight density variations in the primordial plasma. As the universe expanded and cooled, these density fluctuations were amplified by gravity, causing regions with slightly higher densities to attract more matter. Gradually, these regions grew denser, forming long, interconnected structures of dark matter. Baryonic matter, which includes ordinary atoms, followed the gravitational pull of dark matter, accumulating along these filaments. As baryonic matter collected, it cooled down and condensed, leading to the formation of stars and galaxies along the filaments. The process is governed by the same gravitational principles that direct the flow of ordinary matter, but dark matter provides the underlying skeleton. Simulations of the universe's evolution, such as those produced by the Millennium Simulation, illustrate how these filaments emerge from initial conditions and evolve over billions of years. They reveal a complex network of filaments interspersed with voids, vast empty regions where very little matter exists. As galaxies form and evolve along these filaments, their interactions, mergers, and gravitational effects further shape the cosmic web. Filaments act as cosmic highways, guiding the movement of gas and galaxies toward denser nodes where galaxy clusters reside. This continual flow enhances the richness and complexity of the cosmic web, illustrating a dynamic and interconnected universe. Thus, galactic filaments are essential for understanding the large-scale structure of the universe. They not only reveal the distribution of matter, but also shed light on the gravitational and evolutionary processes that have sculpted the cosmos into the vast and captivating tapestry we observe today. Superclusters of galaxies are among the largest known structures in the universe, each containing tens of thousands of galaxies spread across hundreds of millions of light-years. These colossal assemblies present significant challenges and intriguing complexities to our understanding of cosmic structure. First and foremost, their sheer scale and mass concentration push the boundaries of current models of structure formation, requiring more sophisticated simulations and theories that account for such substantial accumulations of matter. One of the primary challenges superclusters pose is their formation and evolution within the framework of the Big Bang and cosmic inflation theories. According to our current understanding, the early universe underwent rapid expansion, smoothing out initial irregularities in the density distribution of matter. Over time, gravity amplified these slight variations, leading to the clustering of matter into galaxies and larger conglomerates. However, the existence of superclusters necessitates that these initial density fluctuations were adequately significant and well distributed to eventually coalesce into such massive structures. This requires precise fine-tuning in our models of initial conditions and particle physics, especially those concerning dark matter and dark energy, which drive cosmic evolution. Additionally, superclusters challenge our comprehension of cosmic flows and gravitational interactions on grand scales. These vast structures influence the motion of galaxies far beyond their immediate regions through their immense gravitational pull, contributing to phenomena such as the cosmic microwave background anomalies and the peculiar velocities of galaxies. Observations of superclusters, such as the Sloan Great Wall and the Laniakea supercluster, which contains our own Milky Way, show that these structures are not isolated but are interconnected by the cosmic web. Understanding the dynamics within and between superclusters involves examining how they funnel and redistribute matter, their interaction with dark matter, and how they evolve over billions of years. Research on superclusters also provides vital clues about the role of dark energy, the mysterious force driving the accelerated expansion of the universe. The distribution and the gravitational effects of superclusters contribute to measuring the overall rate of this expansion and help refine our models of dark energy's influence. Thus, studying superclusters not only enhances our grasp of cosmic structures, but also propels our understanding of fundamental cosmological principles, inviting continuous inquiry and advancements in both observational and theoretical astrophysics. The Great Attractor is a gravitational anomaly located in the direction of the constellation Centaurus, approximately 150 to 200 million light-years from Earth. This mysterious region exerts a significant influence on the motion of galaxies, including our own Milky Way, within a region spanning hundreds of millions of light-years. Discovered through the peculiar velocities of galaxies, deviations from the predicted expansion rate of the universe, the Great Attractor appears to be a gravitational focal point, pulling clusters of galaxies towards it, including the Milky Way, the Andromeda Galaxy, and the entire local group. What makes the Great Attractor particularly fascinating and challenging to study is its location in the zone of avoidance, a region of the sky heavily obscured by the plane of the Milky Way, filled with thick clouds of gas and dust. This obscuration means that traditional optical telescopes struggle to peer into this area, necessitating the use of X-ray and radio observations to gather data. Research indicates that the Great Attractor aligns with the center of the Laniakea supercluster, a vast supercluster of galaxies to which our galaxy belongs. The gravitational influence of the Great Attractor causes observable peculiar velocities that deviate significantly from the uniform expansion predicted by Hubble's law. Galaxies, including our own, are moving towards this region at substantial velocities, on the order of several hundred kilometers per second. This immense pull suggests that the Great Attractor contains a significant amount of mass, far greater than what can be accounted for by visible matter alone. It likely harbors massive galaxy clusters and an even more substantial quantity of dark matter, the unseen substance that makes up about 85% of the total mass of the universe. Understanding the Great Attractor is crucial for a more complete picture of our cosmic neighborhood, as it influences the trajectory and evolution of galaxies over vast distances and timescales. Ongoing advancements in technology and observational techniques continue to reveal more about this massive, hidden force, shedding light on the intricate gravitational landscape of the universe and refining our models of cosmic flow and structure formation. Dwarf galaxies, which are small galaxies containing anywhere from a few million to a few billion stars, frequently interact with larger galaxies like the Milky Way through a variety of gravitationally driven processes. These interactions can significantly influence both the dwarf galaxies and their more massive counterparts. One of the most common outcomes is the phenomenon of galactic cannibalism, where the gravitational pull of a larger galaxy captures and eventually assimilates a dwarf galaxy. This process is observed through elongated streams of stars and gas, known as tidal streams, which trail behind the dwarf galaxy as it is gradually torn apart. The Milky Way's satellite dwarf galaxies, such as the Magellanic Clouds, provide vivid examples of these interactions. As these smaller galaxies orbit the Milky Way, tidal forces exerted by the Milky Way's gravitational field can strip away stars, gas, and dark matter from the dwarfs. This material often forms bridges or tails connecting the two galaxies, such as the Magellanic Stream, a vast ribbon of gas extending from the Magellanic Clouds. These interactions are not only destructive, they can also instigate star formation. For instance, as gas is stripped from the dwarf galaxy and funneled into the larger galaxy, it can compress, creating pockets of increased density that collapse to form new stars. Dwarf galaxies also play a significant role in the evolution of their larger host galaxies. The accretion of a dwarf galaxy can add fresh material to the larger galaxy's halo, influencing its overall mass and potentially triggering periods of active star formation. This process contributes to the growth and evolution of the host galaxy over cosmic timescales. The assimilated stars from dwarf galaxies can alter the chemical composition and the dynamics of the larger galaxy's halo. It is through these frequent mergers and interactions that larger galaxies like the Milky Way have grown and evolved over billions of years. Additionally, studying the distribution and dynamics of dwarf galaxies around the Milky Way helps astronomers understand the underlying dark matter structure. The orbits of dwarf galaxies and the pattern of their tidal disruption offer indirect clues about the dark matter halo of the Milky Way. These interactions are a key component of the hierarchical model of galaxy formation, which posits that large galaxies are built up from smaller building blocks through successive mergers and accretions. The ongoing study of these interactions provides critical insights into the complex and dynamic processes that shape galaxies across the universe. Supernovae are colossal explosions that signify the catastrophic end of a star's life, releasing vast amounts of energy, light, and heavy elements into space. These explosive events are critical to the cosmic cycle of matter and play a significant role in the evolution of galaxies. The primary causes of supernovae are related to two main types: core collapse supernovae and thermonuclear supernovae, each arising from different progenitor stars and mechanisms. Core collapse supernovae, also known as Type II, Type Ib, and Type IC supernovae, occur in massive stars, typically those with a mass greater than 8 times that of the Sun. In these stars, nuclear fusion reactions create increasingly heavier elements in the core, from hydrogen up to iron. Once the core is primarily iron, fusion can no longer release energy, leading to the core's collapse under its own gravity. This collapse happens in a matter of seconds, resulting in a shockwave that propagates outward, ultimately causing the star to explode as a supernova. The distinctions between Type II, Type Ib, and Type IC supernovae depend on the star's outer layers before the explosion. Type II retains its hydrogen envelope, while Types Ib and IC have lost their hydrogen, with Type IC losing even its helium layer. Thermonuclear supernovae, or Type Ia supernovae, occur in binary star systems where one of the stars is a white dwarf, a dense remnant of a star that has exhausted its nuclear fuel. If the white dwarf accrues enough material from its companion star, either through accretion or via a merger, it can reach a critical mass, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. At this point, the pressure becomes so intense that runaway nuclear reactions ignite in the core, causing the entire white dwarf to explode in a thermonuclear fireball. Unlike core collapse supernovae, Type Ia supernovae exhibit a consistent peak brightness, making them crucial standard candles for measuring cosmic distances and studying the expansion rate of the universe. While both types of supernovae result from fundamentally different processes, they share the common trait of enriching the interstellar medium with heavy elements. These elements, ranging from carbon to iron and beyond, are crucial for forming new stars, planets, and ultimately, the building blocks of life. Thus, supernovae are essential not only for understanding stellar life cycles, but also for comprehending the broader processes of cosmic evolution and chemical enrichment in the universe. Neutron stars are formed from the remnants of massive stars that have undergone supernova explosions. During the catastrophic collapse of a supernova, if the core of the original star has a mass between approximately 1.4 and 3 times that of the Sun, it becomes an extraordinarily dense object known as a neutron star. This occurs after the star has exhausted its nuclear fuel, leading to a sequence of events where the core implodes under gravity, and protons and electrons combine to form neutrons, resulting in a nucleus held together by neutron degeneracy pressure. The properties of neutron stars are nothing short of extraordinary. These stellar remnants typically have masses between 1.4 and roughly 2.0 solar masses, but measure only about 10 to 15 kilometers in diameter, making them some of the densest objects in the universe. A single teaspoon of neutron star material would weigh around 1 billion tons. This incredible density means that under the extreme gravitational forces involved, the matter inside a neutron star resides in an exotic state, not found elsewhere in the cosmos. Neutron stars also possess incredibly powerful magnetic fields, which can be trillions of times stronger than Earth's magnetic field. This magnetic intensity can accelerate charged particles to astonishing speeds, resulting in the emission of high-energy radiation, such as X-rays or gamma rays. Some neutron stars are also observed as pulsars, rotating neutron stars emitting beams of electromagnetic radiation from their magnetic poles. As the neutron star spins, these beams sweep across space, and if aligned correctly with Earth, they appear as periodic pulses, hence the name pulsars. Some pulsars can spin at phenomenal rates, over several hundred rotations per second. Additionally, the surface gravity of a neutron star is immensely strong, around 100 billion times that of Earth. This extreme gravity can warp the space-time around the neutron star, creating measurable effects predicted by general relativity. Neutron stars also emit gravitational waves, especially during the violent events leading to their creation, such as the merger of 2 neutron stars or a neutron star merging with a black hole. These events have been detected by observatories like LIGO and Virgo, offering a novel way to study these fascinating objects. The study of neutron stars provides invaluable insights into the fundamental properties of matter under extreme conditions. These cosmic laboratories help astronomers and physicists probe the interactions of particles and forces at densities and energies unavailable in terrestrial laboratories, pushing the boundaries of our understanding of physics. Magnetas are a special type of neutron star with extraordinarily powerful magnetic fields, among the most intense observed in the universe. While typical neutron stars already possess strong magnetic fields, magnetars take this to an astonishing level, with magnetic field strengths reaching up to 1,000 trillion Gauss. For perspective, Earth's magnetic field is about half a Gauss, and a typical neutron star's field might be around 10 to 100 million Gauss. The formation of a magnetar begins similarly to other neutron stars, originating from the collapse of a massive star during a supernova explosion. However, the progenitor star of a magnetar is thought to have certain conditions, such as rapid rotation and specific internal dynamics, which may amplify the magnetic field to extreme levels. The exact process that leads to the formation of such intense magnetic fields is still a topic of active research. One leading theory suggests that these fields are generated through a dynamo process during the first few seconds after the neutron star's birth, where the rapid rotation and convection within the star amplify the existing magnetic field. The extreme magnetic fields of magnetars have profound effects on their surrounding environments. These fields are so intense that they can distort the shape of atoms and influence the quantum vacuum, creating phenomena like vacuum birefringence, where the vacuum behaves as a birefringent medium due to the presence of a strong magnetic field. Magnetars also exhibit dramatic and violent magnetic activity, producing bursts and flares of X-rays and gamma rays. These bursts result from the instability and reconnection of magnetic field lines, which can release an enormous amount of energy in a very short time. Magnetars are responsible for some of the most energetic phenomena observed, such as soft gamma-ray repeaters and anomalous X-ray pulsars. SGRs are known for their episodic bursts of hard X-rays and soft gamma rays, which can outshine all other X-ray sources in the sky for a short period. One of the most famous events, recorded in 2004 from the magnetar SGR 1806-20, emitted more energy in a fraction of a second than the Sun emits in 100,000 years. The study of magnetars not only helps us understand the exotic states of matter and magnetic fields under extreme conditions, but also provides insights into the behavior of fundamental particles and quantum field interactions in unparalleled cosmic laboratories. These powerful celestial objects continue to challenge our understanding of physics and the dynamics of stellar evolution. In binary star systems, mass exchange can occur when one star expands and its outer layers overflow its Roche lobe, the region around a star within which orbiting material is gravitationally bound to that star. This overflow happens predominantly in close binary systems, where the stars are sufficiently near each other. The mass transfer process can have profound consequences for the evolutionary paths of both stars in the system. The most common scenario for mass exchange involves a red giant or supergiant star that expands as it evolves off the main sequence. Once this star fills its Roche lobe, its material can start flowing towards its companion star, which may or may not have evolved significantly. The receiving star can accrete this material, potentially forming an accretion disk if it is a compact object like a white dwarf, neutron star, or black hole. This accretion disk emits significant amounts of energy, often seen in X-ray binaries, where the accreting object is a neutron star or black hole. One significant consequence of mass transfer is the alteration of the stellar and orbital characteristics of both stars. The donor star loses mass, which can significantly shorten its life cycle and drive it into different evolutionary paths, like becoming a white dwarf or shifting into a helium-burning phase far quicker than it otherwise would. The accreting star gains mass, which can lead to rejuvenation if the star was initially of lesser mass, allowing it to burn hydrogen again as a more massive star. If the accreting star is a white dwarf, the process can lead to explosive outcomes. For instance, if a white dwarf in a binary system gains enough material to approach the Chandrasekhar limit, about 1.4 solar masses, it can ignite runaway nuclear fusion, culminating in a Type Ia supernova. This type of supernova is crucial for measuring cosmic distances due to its predictable luminosity. Another outcome of mass transfer can be the formation of peculiar stars, such as blue stragglers. These stars appear younger and hotter than their counterparts in the same cluster and are believed to have formed through the mass transfer process, where the gained material causes them to evolve differently than other coeval stars. Mass transfer also dynamically affects the orbital characteristics of the binary system. As mass is transferred from the donor star to the accretor, the system's center of mass shifts, often altering the orbital period and eccentricity. In cases where a significant amount of mass is lost to the interstellar medium, the system can experience a reduction in total mass, leading to an increase in orbital separation. Overall, mass exchange in binary star systems is a complex and transformative process that can lead to a variety of astrophysical phenomena, significantly altering the evolution of the stars involved and contributing to energetic events that impact the surrounding cosmic environment. Brown dwarfs occupy an intriguing niche in the universe, positioned between the largest planets and the smallest stars. These celestial objects, often referred to as failed stars, are fascinating due to their inability to sustain traditional nuclear fusion. When a star forms, it must accumulate enough mass to ignite hydrogen fusion in its core, which requires a mass of at least 75 times that of Jupiter. Brown dwarfs, however, typically weigh in at only a fraction of this threshold, usually between 13 and 65 Jupiter masses. Because brown dwarfs cannot maintain the sustained hydrogen fusion that powers stars like our Sun, they emit a dim, reddish glow instead of the bright radiance of a typical star. Despite their moniker, brown dwarfs still experience a form of fusion. They can fuse deuterium, a heavier isotope of hydrogen, and in some cases lithium. However, this fusion is short-lived and insufficient to classify them as full-fledged stars. Their temperatures and luminosities lie between those of stars and gas giant planets, making them critical subjects for studying the boundary between stellar and planetary formation. They are not just cosmic failures. They provide essential insights into the complexity of the universe's birthed objects. Massive stars, those with more than 8 times the mass of our Sun, are the cosmic forges in which heavy elements are produced through a process known as nucleosynthesis. These fiery giants undergo a series of fusion reactions in their cores, starting with hydrogen fusion that converts hydrogen into helium. As these stars age and deplete their hydrogen fuel, they climb the fusion ladder, sequentially burning heavier elements in their cores through increasingly complex nuclear reactions. When a massive star exhausts its core hydrogen, it begins to fuse helium into carbon and oxygen. As these elements accumulate, the star contracts under gravity and its core temperature rises, reaching levels necessary to fuse carbon into heavier elements like neon, magnesium, and silicon. This escalating chain of fusion continues, forming progressively heavier elements until iron is produced in the core. Iron fusion, unlike the previous stages, does not yield energy. Instead, it consumes energy, leading to a halt in the exothermic fusion processes that have powered the star until this point. The creation of elements heavier than iron occurs during the explosive death throes of massive stars. When the core collapses under its own gravity, it triggers a supernova explosion, releasing an immense amount of energy and a barrage of neutrons. These neutrons are captured by atomic nuclei in a process called neutron capture, creating elements such as gold, uranium, and platinum. The force of the supernova disperses these newly forged elements into the cosmos, seeding future generations of stars, planets, and the life that may grow upon them. In this spectacular manner, massive stars are the crucibles that enrich the universe with the raw materials necessary for the complex structures and life forms we observe today. A pulsar is a highly magnetized rotating neutron star born from the remnants of a supernova explosion. When a massive star exhausts its nuclear fuel, its core collapses under gravity, squeezing protons and electrons together to form neutrons. This collapse results in an incredibly dense object, often no more than 20 kilometers in diameter, yet possessing the mass of 1 to 2 suns. What sets a pulsar apart from other neutron stars is its intense magnetic field, which can be over 1 trillion times stronger than Earth's. This magnetic field accelerates charged particles near the star's magnetic poles, causing them to emit beams of electromagnetic radiation, often in the form of radio waves. Due to the misalignment between the star's rotation axis and its magnetic axis, these beams sweep across space like the beams of a lighthouse. When one of these beams points toward Earth, it is detected as a pulse of radiation. The regularity of these pulses is remarkable, often acting like cosmic clocks with precision unmatched by any human technology. This consistency originates from the neutron star's rapid rotation, which can be anywhere from a few times per second to over 600 times per second. As the neutron star rotates, its intense gravitational and magnetic fields ensure that the emission mechanism remains stable, resulting in incredibly regular pulse intervals. These periodic signals allow astronomers to gain insights into the properties of neutron stars, measure cosmic distances, and even test the theories of general relativity. Pulsars, therefore, not only captivate us with their rhythmic emissions, but also serve as indispensable tools in the exploration of our universe. Stellar nurseries, also known as molecular clouds, are vast regions of gas and dust where new stars are born. These clouds are primarily composed of hydrogen molecules mixed with traces of other elements and compounds. The formation of new stars within these nurseries begins with the cooling and condensation of these dense molecular clouds. Over time, regions within the cloud experience gravitational instabilities, causing them to collapse under their own weight. For new stars to form, several conditions must be met. First, the molecular cloud needs to be sufficiently dense, which allows for the accumulation of enough material to eventually ignite nuclear fusion. The cloud must also be cold, typically around 10 to 20 Kelvin degrees above absolute zero, as lower temperatures facilitate the formation of molecular hydrogen, the primary building block of new stars. Additionally, turbulence within the cloud can lead to the creation of clumps, which become the seeds for star formation. When these clumps reach a critical mass, gravity takes over, pulling in more gas and increasing the pressure and temperature at the core. As the core of a collapsing clump reaches temperatures of approximately 1 million Kelvin degrees, nuclear fusion ignites, converting hydrogen into helium and releasing energy in the process. This energy creates an outward pressure that opposes the inward pull of gravity, leading to the formation of a new protostar. Over time, the protostar continues to accrete material from its surroundings, growing in mass and luminosity until it reaches equilibrium as a main sequence star. Throughout this journey, the surrounding gas and dust are either incorporated into the forming star or pushed away by stellar winds and radiation, often creating spectacular nebulous structures that mark the birthplace of new stars. Thus, stellar nurseries are essential cradles of cosmic evolution, transforming cold, dark clouds into the brilliant stars that illuminate our night sky. These birthplaces are not just sites of star creation, but also laboratories for understanding the fundamental processes that govern the life cycles of stars and the overall dynamics of galaxies. A Wolf-Rayet star is a remarkable and exceptionally rare type of star, distinguished by its extreme temperatures, powerful winds, and prominent spectral lines, indicating a high degree of ionization. These stars represent a late stage in the evolution of massive stars, typically those with initial masses greater than 20 times that of our Sun. Removing their outer hydrogen layers through intense stellar winds, Wolf-Rayet stars expose their hot, helium-rich cores. The scarcity of Wolf-Rayet stars stems from the rapid and tumultuous evolutionary path they undergo. Only a small fraction of massive stars ever reach this stage because the conditions required for a star to become a Wolf-Rayet are both specific and fleeting. These stars burn through their fuel at an astonishing rate, living fast and dying young. As a result, they spend only a few 100,000 years in the Wolf-Rayet phase, a mere blink in astronomical terms compared to the millions or even billions of years that lower-mass stars like our Sun may live. One of the hallmarks of Wolf-Rayet stars is their powerful stellar winds, which can eject material at speeds of up to several thousand kilometers per second. These winds strip the star of its outer layers, enriching the surrounding interstellar medium with heavy elements. This shedding of mass leads to spectacular surrounding nebulae formed from the ejected material illuminated by the intense radiation of the Wolf-Rayet star itself. The end fate of these stars is often as cataclysmic as their lives are intense. Most Wolf-Rayet stars are expected to end their lives in dramatic supernova explosions, potentially leading to the formation of black holes or neutron stars. The rarity of Wolf-Rayet stars lies in their extreme and ephemeral nature. They are not only key to understanding the life cycles of the most massive stars, but also crucial contributors to the chemical enrichment and dynamical processes in galaxies, serving as both creators and destroyers in the cosmic landscape. In the complex dance of binary star systems, some stars engage in a dramatic and often destructive process known as stellar vampirism. This phenomenon occurs when one star, typically a more massive and evolved companion, begins to siphon material from its partner. These binary systems contain two stars closely orbiting each other, and as they evolve, their interactions become increasingly dynamic and in some cases predatory. The process of stellar vampirism usually starts when the more massive star evolves and expands into a red giant, causing its outer layers to overflow its gravitational boundary, known as the Roche lobe. When the outer material of the red giant crosses this boundary, it spirals towards the gravitational pull of the smaller, denser companion star. This companion, often a white dwarf, neutron star, or even a black hole, then accretes the captured gas and dust onto its surface or into a surrounding accretion disk. The infalling material from the donor star can drastically alter the physical properties and evolutionary trajectories of both components in the system. For example, the mass-gaining star may experience increased luminosity and temperature, undergoing periods of intense activity and radiative outbursts. Meanwhile, the donor star may become significantly stripped of its outer layers, eventually exposing its core and altering its own evolutionary path. In some extreme cases, the vampirized star can be entirely consumed or reduced to a much less massive remnant. This transfer of material not only affects the star's lives, but can also result in spectacular cosmic phenomena. For instance, when a white dwarf in such a binary system accumulates enough material, it may trigger a thermonuclear runaway reaction, leading to a Type Ia supernova, an event crucial for understanding cosmic distances due to its consistent luminosity. Thus, the dramatic interplay of stellar vampirism showcases the perilous and intertwined fates of stars in binary systems, illustrating yet another captivating aspect of the universe's continuous cycle of creation, destruction, and transformation. The Fermi paradox is the apparent contradiction between the high probability of extraterrestrial civilizations existing in our vast galaxy and the lack of any evidence or contact with such civilizations. Named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights the discrepancy between the mathematical likelihood of intelligent life elsewhere and the silence we encounter within our extraterrestrial searches. One potential solution to the Fermi paradox is the rare Earth hypothesis, which suggests that a combination of rare and complex factors have conspired to make Earth uniquely suitable for life. These factors include the planet's stable climate, its magnetic field that deflects harmful cosmic rays, the presence of liquid water, and the stabilizing influence of Jupiter, which reduces the impact rate of comets and asteroids. This hypothesis implies that, while microbial life might be common, the evolution of intelligent life is an extraordinarily rare event. Another intriguing solution is the Great Filter theory, which postulates that there is some critical stage in the evolution of life that is extremely unlikely to be surpassed. This filter could exist at various points, such as the emergence of life itself, the development of simple cells into complex organisms, or even the transition from advanced civilizations to spacefaring societies capable of interstellar communication. The Great Filter suggests that either we have already passed this improbable hurdle, making us unique, or it lies ahead of us, posing a significant threat to our long-term survival. Other solutions entertain the possibility that extraterrestrial civilizations are intentionally avoiding us. This could be due to self-imposed quarantine to protect less advanced species, similar to the Prime Directive in science fiction, or because they use communication technologies or strategies we do not yet understand. Another proposition is the simulation hypothesis, where our perceived reality is an artificial simulation, and the absence of contact with extraterrestrial beings is a parameter set by the creators of this simulated reality. These theories, among others, reflect the profound complexity and mystery inherent in the search for extraterrestrial intelligence. They encourage us to look inward at our assumptions and outward with ever greater curiosity, driving both scientific inquiry and philosophical reflection about our place in the cosmos. Fast radio bursts, or FRBs, are enigmatic, intense bursts of radio waves that last only milliseconds yet release as much energy as the sun emits in a day. First discovered in 2007, these fleeting phenomena have since posed significant challenges to our understanding of the universe due to their mysterious origins and extreme energy scales. The brevity and sheer power of FRBs have left astronomers puzzled and opened up new avenues of inquiry into some of the most energetic processes in the cosmos. One of the major challenges FRBs present is pinpointing their exact sources. The short duration and unpredictable occurrence make them difficult to localize with precision. Initial detections were thought to be random, single events coming from vast distances outside our galaxy. However, the discovery of repeating FRBs has added layers of complexity to the puzzle. These repeaters suggest that, unlike cataclysmic one-off events like supernovae, there could be some mechanism or environment capable of producing multiple bursts. Possible sources range from highly magnetized neutron stars called magnetars to exotic scenarios involving black holes or even hypothetical alien technologies. The extreme distances over which FRBs travel also provide a unique tool for probing the intergalactic medium, the sparse hydrogen and helium gas that lies between galaxies. As FRBs journey through this medium, their radio waves interact with the free electrons they encounter, causing dispersion. By analyzing this dispersion effect, scientists can infer properties of the intergalactic medium and potentially uncover details about the distribution of matter in the universe. Fast radio bursts challenge existing astrophysical models, and encourage the development of new theories to explain such high-energy, short-duration events. Additionally, they underscore the limitations of current observational technologies and the need for more sophisticated instruments capable of capturing these elusive signals. The study of FRBs thus holds the promise of not only solving a captivating cosmic mystery, but also of yielding deeper insights into the universe's fundamental structure and the extreme environments that inhabit it. The Great Silence refers to the perplexing absence of signals or evidence of extraterrestrial civilizations, despite the vastness of the universe and the high probability that life should exist elsewhere. This enigma is intertwined with the Fermi paradox and continues to puzzle astronomers, scientists, and thinkers alike. Given the age of the Milky Way galaxy, about 13 billion years, and the sheer number of potentially habitable planets, there has been ample time for advanced civilizations to arise and make their presence known. Yet we hear nothing, no messages, no probes, no signs of alien infrastructure. One explanation for the Great Silence is the rare Earth hypothesis, which posits that the conditions that foster intelligent life are extremely rare or unique to our planet. This would imply that intelligent civilizations are far less common than we suppose, possibly leaving us in splendid isolation in a mostly barren cosmos. Another theory, often dubbed the zoo hypothesis, suggests that advanced extraterrestrial civilizations might be intentionally avoiding contact with us, much like humans observe animals in a zoo without disturbing them. This could be due to a number of reasons, ranging from ethical considerations to a desire to observe our development without interference. The Great Filter hypothesis offers another unsettling explanation. It suggests that there is some critical stage in the development of life that is extremely difficult to surpass. This could be the emergence of intelligent life, the ability to achieve sustainable technological advancement, or even the avoidance of self-destruction. If the Great Filter is ahead of us, it could imply that most civilizations self-destruct before achieving interstellar communication or travel, explaining the eerie silence we observe. Then there's also the possibility that we are not listening properly or in the right ways. Advanced civilizations might be using communication methods or technologies far beyond our current understanding and capabilities, making their signals undetectable with our present instruments. Furthermore, the vast distances and timescales involved in space could mean that signals are rare and take eons to travel, or they are directed in ways and areas we have not yet explored. The Great Silence remains one of the most profound and thought-provoking mysteries in astronomy and science, continuously challenging our assumptions about life, intelligence, and our place in the universe. It invites endless speculation and drives efforts to develop more sophisticated means of detecting potential cosmic neighbors, keeping the quest for extraterrestrial contact as one of the most compelling scientific endeavors of our era. The observation that some galaxies rotate faster than our models predict has been one of the most compelling mysteries in modern astrophysics, leading to significant developments in our understanding of the universe. According to classical Newtonian mechanics and the visible matter present in galaxies, the outer stars should orbit more slowly than they actually do. However, observations, particularly of spiral galaxies, reveal that the rotational speeds of stars in the outer regions remain relatively constant or even increase compared to what would be expected if only visible matter were influencing their motion. This discrepancy led to the postulation of dark matter, an unseen component that does not emit, absorb, or reflect light, making it invisible through conventional electromagnetic observations. Dark matter is believed to account for approximately 27% of the universe's mass-energy content, compared to just about 5% from ordinary visible matter. Its gravitational influence is thought to provide the extra mass necessary to explain the unexpected rotational speeds. Essentially, dark matter forms a vast invisible halo around galaxies, whose gravitational pull keeps the outer stars moving at higher velocities. Various lines of evidence support the existence of dark matter, including its effects on the cosmic microwave background radiation, gravitational lensing, where massive objects bend the path of light from distant objects, and the large-scale structure of the universe. However, dark matter has eluded direct detection, remaining one of the most compelling yet elusive topics in astrophysical research. Efforts to detect dark matter particles are underway in facilities worldwide, utilizing sophisticated detectors deep underground to shield them from cosmic radiation and other potential interferences. Alternatively, some scientists have explored modifications to our understanding of gravity itself. The theory of modified Newtonian dynamics suggests that the laws of gravity might change under low acceleration conditions found at the edges of galaxies. While MOND can explain some galactic rotation curves without invoking dark matter, it struggles to account for other observations, especially those on larger cosmological scales, where dark matter theory still holds stronger explanatory power. The surprisingly fast rotation of galaxies has significantly deepened our understanding of the cosmos, pointing towards a large amount of unseen mass that shapes galactic dynamics. Whether this mystery is fully resolved by dark matter, modifications to our theories of gravity, or some other yet-to-be-discovered phenomenon, it remains a critical question driving research efforts and reshaping our understanding of the universe's fundamental nature. The WOW signal is one of the most intriguing and mysterious radio signals ever detected from space, capturing the imagination of astronomers and the public alike. On August 15, 1977, Dr. Jerry R. Amon, using the Big Ear radio telescope at Ohio State University, recorded a strong, narrowband radio signal that appeared to originate from the constellation Sagittarius. The signal lasted for 72 seconds, the maximum time the Big Ear could observe it, and was significantly stronger than the background noise. Dr. Amon was so impressed by the signal's characteristics that he circled it on the printout and wrote "WOW" in the margin, giving the signal its now famous name. The WOW signal has never been fully explained for several reasons. First, despite numerous attempts to detect a similar signal from the same region of the sky, the WOW signal has never been repeated, which makes it challenging to study it further or draw definite conclusions about its source. Astronomers consider recurring signals to be more easily investigated because they can be subjected to repeated observations and tests from multiple locations and instruments. The absence of a repeat signal leaves scientists to work with the data from the brief window of its initial detection. Various hypotheses have been proposed to explain the WOW signal, ranging from natural astrophysical phenomena to artificial sources. Natural explanations include reflections from Earth satellites or asteroid emissions, but these do not satisfactorily account for the signal's specific characteristics. On the other hand, the possibility of it being an artificial transmission from an extraterrestrial civilization tantalizes researchers, as the signal's properties align with what one might expect from an interstellar communication attempt. Specifically, it was a narrowband signal centered around the 1420 MHz frequency, which is significant because it is the natural emission frequency of neutral hydrogen, the most abundant element in the universe, and an ideal hailing frequency for interstellar communication. Despite the excitement, the non-recurrence of the signal and the lack of corroborating evidence from other observatories means that any claim of it being a message from extraterrestrials remains speculative. Additionally, various technical limitations of the Big Ear telescope when the signal was detected mean that there are gaps in the recorded data, further complicating attempts to draw definitive conclusions. The WOW signal remains an open question in the scientific community, symbolizing both the promise and the challenge of the search for extraterrestrial intelligence. While it has not provided concrete evidence of alien life, it continues to inspire curiosity and drive efforts to build more advanced methods and instruments to explore the enigmatic cosmos. The observation that some stars appear older than the universe poses a perplexing paradox that has puzzled astronomers and astrophysicists for years. The age of the universe is currently estimated to be about 13.8 billion years, based on measurements of the cosmic microwave background radiation and the expansion rate of the universe. However, some stars, particularly ancient ones in globular clusters, have exhibited characteristics that suggest they might be older than this calculated age. One of the primary methods for determining the age of a star involves studying its composition through spectroscopy. Heavier elements, known as metals in astronomical terms, are produced by previous generations of stars. Therefore, a star with very low metallicity is considered to be one of the earliest stars, formed when the universe was still in its infancy. Another method involves examining the star's position on the Hertzsprung-Russell diagram, which illustrates the relationship between a star's luminosity and its temperature. By understanding a star's life cycle, scientists can estimate its age. The paradox of seemingly impossibly old stars arises from several potential sources of error or misunderstandings. One possibility is that our models of stellar evolution might need refinement. For instance, if we have not accurately accounted for all the physical processes affecting a star's life cycle, our age estimates could be off. Additionally, uncertainties in measurements of distance, luminosity, and other factors can also lead to inaccurate age calculations. Another crucial factor is the determination of the Hubble constant, the rate at which the universe is expanding. This value has varying estimates depending on the method used, and even small discrepancies can lead to significant differences in the calculated age of the universe. Reconciling these differences is an ongoing challenge in cosmology, and efforts like the Hubble Space Telescope's observations and those expected from the James Webb Space Telescope aim to refine our measurements further. Moreover, advancements in understanding dark energy and dark matter, which constitute a significant portion of the universe's mass energy content, could provide new insights that help resolve this paradox. As our tools and models improve, we anticipate harmonizing the apparent discrepancy between the ages of the oldest stars and the age of the universe itself. In conclusion, while the appearance of stars older than the universe's estimated age introduces a fascinating conundrum, it simultaneously drives the scientific community to develop more precise instruments and sophisticated models, deepening our understanding of both stellar evolution and the cosmos itself. The Shapley supercluster is one of the largest and most massive structures in the observable universe, located approximately 650 million light-years away from Earth in the direction of the constellation Centaurus. Named after the American astronomer Harlow Shapley, who was instrumental in our understanding of the scale and structure of the universe, this supercluster is thought to contain around 8,000 galaxies, making it extraordinarily dense and massive. The Shapley supercluster's immense gravitational pull plays a significant role in influencing the motion of our Milky Way galaxy, as well as our local galactic neighborhood. The combined mass of the galaxies, dark matter, and interstellar gas within the Shapley supercluster creates a gravitational well that contributes to a peculiar velocity pattern observed in the universe's local region. Our Milky Way galaxy, along with the rest of the local group, is being pulled toward a mysterious region known as the Great Attractor. The Great Attractor is a gravitational anomaly located approximately 150 to 250 million light-years away in the vicinity of the Hydra Centaurus supercluster, but pointing toward the direction of the Shapley supercluster. The gravitational influence from the Shapley supercluster adds additional complexity to this large-scale motion. While the Great Attractor significantly influences the Milky Way's motion, the Shapley supercluster's gravitational forces are thought to contribute an additional component to this motion, accelerating our local supercluster towards it. Essentially, our galaxy's movement through space can be seen as a result of the combined gravitational pulls from both the Great Attractor and more distant massive structures like the Shapley supercluster. Understanding these gravitational influences helps astronomers map out the large-scale structure of the universe and track the dynamic movements of galaxies within it. This motion is not merely a local phenomenon, but contributes to the grander narrative of cosmic evolution, where galaxies and clusters interact in a dance governed by gravity over billions of years. The Shapley supercluster, with its vast assemblage of galaxies and immense gravitational influence, plays a crucial role in shaping the motion of our Milky Way and its neighbors. By studying such gargantuan structures, astronomers seek to better understand the web of gravitational forces that tie together the cosmos, offering insights not just into our galactic neighborhood, but into the broader mechanics of the universe. The geological activity observed on some planets and moons in our solar system is unexpected and fascinating, challenging our understanding of planetary science and geophysics. Traditionally, significant geological activity, such as volcanism, tectonics, and cryovolcanism, was expected to occur primarily on larger, warmer bodies like Earth. However, data from space missions have unveiled a variety of dynamic geological processes on smaller and colder moons and dwarf planets, suggesting that geological activity is far more widespread and diverse than previously thought. One prominent example is Jupiter's moon Io, which is the most volcanically active body in the solar system. Io's intense geological activity results from tidal heating, driven by the gravitational interactions with Jupiter and neighboring moons Europa and Ganymede. These gravitational forces create significant internal friction, heating Io's interior and causing continuous volcanic eruptions, some of which are so powerful they send plumes hundreds of kilometers into space. Saturn's moon Enceladus offers another intriguing case. Despite its small size and distance from the Sun, Enceladus exhibits geysers that spew water vapor and ice particles from its south polar region. These plumes are evidence of subsurface oceans beneath an ice crust, kept in a liquid state by heat generated from tidal interactions with Saturn. The discovery of organic compounds in these plumes raises tantalizing possibilities about the potential for life in these hidden oceans. Similarly, Neptune's moon Triton shows signs of cryovolcanism, where volcanic activity involves water, ammonia, or methane instead of molten rock. Triton's surface features nitrogen geysers driven by seasonal heating from solar radiation that release plumes of nitrogen gas and dust. This activity provides compelling evidence of internal geological processes previously thought impossible on such a distant and cold moon. Another fascinating object is Pluto, which was revealed by the New Horizons mission to have a surprisingly youthful and varied surface. Features such as ice mountains and vast plains of nitrogen ice suggest ongoing geological processes. The heat driving these activities may come from a combination of radioactive decay in the core and the potential for subsurface oceans maintained by internal heat. These discoveries indicate that our understanding of geological processes must extend beyond the traditional mechanisms observed on Earth. Tidal heating, radioactive decay, and even the peculiar dynamics of icy and rocky materials in various environmental conditions contribute to unexpected geological activity across the solar system. These processes not only reveal the complexity and diversity of planetary geology, but also expand our horizons in the search for potentially habitable environments beyond Earth. The Butter's Void, often referred to simply as the Void, is one of the largest known voids in the universe, a colossal expanse of empty space that spans nearly 330 million light-years in diameter. Located in the Butter's constellation, this void was discovered in 1981 by astronomers Robert Kirshner and his team, who were conducting a survey of galaxy redshifts. The apparent emptiness of this region is so striking that it initially confounded astronomers, as it contains far fewer galaxies than typical regions of the universe. Void regions like the Butter's Void are part of the large-scale structure of the universe, which resembles a cosmic web. This web is composed of filamentary structures of galaxies and clusters of galaxies, with vast empty spaces or voids in between. Voids are thought to form naturally as a result of cosmic inflation and the subsequent gravitational attraction of matter. Over billions of years, gravitational forces pull matter into the filaments and clusters, leaving behind these vast empty regions. The reason the Butter's Void is so empty lies in this process of cosmic evolution. In the early universe, slight density fluctuations caused areas with a bit more matter to pull in even more material due to gravity, creating denser regions. Conversely, regions with slightly less matter became increasingly less dense, forming voids. Over time, these processes amplify, and the matter preferentially moves into the filaments, leaving the voids increasingly empty. The Butter's Void is an extreme example of this process, where matter has been significantly depleted to the extent that it now contains only a few sparse galaxies. Interestingly, despite its vast emptiness, the Butter's Void is not completely devoid of galaxies. It is estimated that there could still be tens of thousands of galaxies within it, but this number is extraordinarily low given the size of the void. For comparison, a similarly sized volume in a more typical part of the universe would contain millions of galaxies. Studying such enormous voids helps astronomers understand more about the dynamics of cosmic evolution and structure formation. By examining the distribution of matter, both visible and dark, within and around voids, researchers can gain insights into the nature of dark matter and dark energy, which govern the large-scale behavior of the universe. The Butter's Void, with its staggering emptiness, serves as a profound reminder of the universe's vastness and the intricate dance of matter influenced by gravity and other fundamental forces. Astronomers have long been puzzled by stars that appear to vanish from their sky maps. One explanation involves a process called significant dimming. Stars may suddenly dim due to clouds of interstellar dust moving between the star and Earth. These clouds can block a substantial portion of the star's light, making it appear as though the star has disappeared. This dimming is temporary. Once the dust cloud moves away, the star reappears, leading to perplexing observations. Another fascinating phenomenon involves what is known as failed supernovae. In such cases, a massive star, at least 18 times the mass of our Sun, collapses directly into a black hole without the spectacular explosion typical of a supernova. When this happens, the star essentially vanishes from observable view because it no longer emits light that can reach Earth. These black holes are extremely difficult to detect, as they do not emit light, and their immense gravitational pull swallows anything that gets too close. Essentially, what astronomers witness is the abrupt disappearance of a once bright star, offering evidence that failed supernovae contribute to our mysterious cosmic neighborhood. Gravitational slingshots, or gravity assists, are ingenious methods allowing spacecraft to travel vast distances with minimal fuel. By carefully plotting a spacecraft's trajectory, mission planners can use the gravitational pull of a planet or moon to accelerate and redirect the spacecraft. As the spacecraft approaches a planetary body, it falls into the planet's gravitational field and gains speed. Just as it is about to be pulled into orbit, it maneuvers to sling around the planet, using the planet's momentum to catapult itself away at a much higher velocity. The technique works on the principle of orbital mechanics and conservation of momentum. When a spacecraft flies close to a planet, it's essentially stealing a minuscule fraction of the planet's orbital energy. Though the planet's velocity change is imperceptible due to its enormous mass, the spacecraft experiences a significant boost in speed. This method has been pivotal in missions to the outer planets. For example, the Voyager probes used gravitational slingshots around Jupiter and Saturn to travel beyond the solar system, reaching speeds unattainable by conventional propulsion alone. This clever interplay of celestial mechanics and human ingenuity allows us to explore distant worlds, pushing the frontier of human knowledge and curiosity. The James Webb Space Telescope represents a monumental leap forward in our ability to observe the cosmos. Scheduled to provide unprecedented images and data, the telescope is equipped with a primary mirror over 21 feet in diameter, nearly 3 times the size of the Hubble Space Telescope's mirror. Its advanced technology includes instruments capable of observing infrared light, allowing scientists to peer through cosmic dust clouds that have obscured our view of star formations and other celestial phenomena. This capacity to capture infrared light is crucial because many objects in space emit more light in the infrared spectrum than in visible wavelengths. One of the most transformative aspects of the JWST is its ability to look back in time. By observing distant galaxies, the telescope can capture light that has traveled billions of years to reach us. Essentially, this means JWST will allow scientists to study the early universe, shedding light on how the first stars and galaxies formed after the Big Bang. Moreover, it will enhance our understanding of exoplanets by analyzing their atmospheres, searching for biosignatures, chemical indicators of life. The power of JWST lies not just in its advanced optics and sensors, but in the vast scope of questions it aims to address, from the origins of the universe to the possibilities of life beyond our solar system. Space probes are marvels of engineering, meticulously designed to endure the treacherous conditions of deep space. These probes must withstand extreme temperatures, ranging from the blistering heat near the Sun to the frigid cold of the outer solar system. Engineers use multi-layered insulation, often made of materials like gold or aluminum foils, to shield delicate instruments from these temperature extremes. Additionally, probes are equipped with heaters to keep vital components at operational temperatures when they venture into the colder regions of space. Radiation is another formidable challenge. Cosmic rays and solar radiation can damage electronic circuits and instrumentation. To safeguard against this, probes are built with radiation-hardened components and often encased in protective shielding. This ensures that the onboard electronics remain functional despite constant exposure to high-energy particles. For instance, the New Horizons probe, which traveled to Pluto and beyond, was designed with robust systems to cope with these harsh conditions. Energy management is crucial for the survival of deep space probes. Solar panels are highly efficient in the inner solar system, but lose effectiveness farther out. Probes venturing into the outer planets and beyond often rely on radioisotope thermoelectric generators, which convert the heat from decaying radioactive material into electricity. This consistent power supply enables the probe to operate its instruments and communicate with Earth over vast distances. Together, these sophisticated measures ensure that space probes can endure and thrive, relaying critical scientific data across the immense void of space. The Breakthrough Starshot project is an ambitious initiative aimed at sending tiny, lightweight probes to our nearest star system, Alpha Centauri, which lies over 4 light-years away. Spearheaded by a team of scientists and backed by significant private funding, the project envisages deploying swarms of small, chip-sized spacecraft called starchips. These starchips would be attached to ultra-thin, light-propelled sails, known as light sails. The concept relies on leveraging powerful ground-based lasers to propel these light sails to remarkable speeds, potentially up to 20% of the speed of light. By aiming focused laser beams at the light sail, the energy pushes the starchip forward, drastically reducing the travel time to Alpha Centauri to about 20 years, compared to the tens of thousands of years it would take with conventional spacecraft. Despite their minuscule size, these starships will be equipped with essential scientific instruments, cameras, and communication devices, enabling them to capture and send back images and data from this distant star system. Achieving such speeds presents numerous technical challenges, including the precise control of the laser beam and the durability of the light sails over extended periods in space. The sails must be capable of withstanding collisions with micrometeoroids and enduring intense radiation. Nonetheless, if successful, the Breakthrough Starshot project would revolutionize our ability to explore other star systems, offering a groundbreaking way to study planets around other stars and potentially identify habitable worlds beyond our solar system. This project symbolizes a significant leap forward in human curiosity and technological prowess, moving us closer to becoming an interstellar species. Space telescopes fundamentally transform our view of the universe by bypassing some critical limitations of ground-based observations. One of the most significant challenges faced by telescopes on Earth is the distortion caused by the Earth's atmosphere. Even the clearest skies scatter and absorb some of the incoming light from celestial objects, leading to blurred and less precise images. Space telescopes operate above the atmosphere, completely eliminating this issue and providing a crystal-clear view of the cosmos. Additionally, the atmosphere blocks certain wavelengths of electromagnetic radiation, such as ultraviolet, X-rays, and the majority of the infrared spectrum. These wavelengths are essential for studying various astrophysical phenomena, from the hot young stars emitting ultraviolet radiation to the cooler, ancient stars and distant galaxies observable in the infrared. For instance, the Hubble Space Telescope has provided remarkable ultraviolet and visible light images, while the James Webb Space Telescope's infrared capabilities will allow astronomers to see through cosmic dust clouds, unveiling regions of star formation and even the atmospheres of exoplanets. Moreover, space telescopes can continuously observe their targets without the interruptions caused by the day-night cycle or weather conditions that ground-based telescopes must contend with. This constant observation capability is crucial for monitoring dynamic events such as supernovae, the movements of celestial objects, or changes in the atmospheres of distant planets. By freeing astronomical observations from terrestrial limitations, space telescopes have not only broadened our understanding of the universe, but also opened up new frontiers in the quest to unravel the mysteries of space. Space junk, also known as space debris, refers to the accumulation of defunct human-made objects in Earth's orbit. This includes spent rocket stages, non-functional satellites, fragments from disintegration, and collisions among other discarded materials. As more missions are launched, this clutter grows, creating a perilous environment akin to a cosmic junkyard. The most significant threat posed by space junk is the risk of collisions with operational spacecraft, satellites, and even the International Space Station. Even tiny fragments of debris traveling at velocities up to 17,000 miles per hour can cause catastrophic damage upon impact. In fact, satellites and the ISS are regularly maneuvered to avoid such collisions, adding complexity and cost to their operation. The danger is not just hypothetical. Several recorded incidents have highlighted the stakes. For example, in 2009, an inactive Russian satellite collided with an operational American communications satellite, producing thousands of additional debris fragments. One of the particularly alarming scenarios is the Kessler syndrome, a theoretical cascade effect where collisions generate more debris, leading to further collisions in a self-perpetuating cycle. This could render certain orbits unusable, jeopardizing future space missions and the sustainability of satellite operations critical for communication, weather forecasting, and navigation. Addressing space junk requires international cooperation and innovative solutions, such as debris removal technologies and better end-of-life disposal strategies for satellites, to mitigate this growing hazard and ensure safe passage for future explorers and their spacecraft. Ion engines, or ion thrusters, represent a transformative propulsion technology that offers unique advantages for deep space missions. Unlike conventional chemical rockets, which rely on explosive fuel combustion to generate thrust, ion engines operate by ionizing a propellant, typically xenon gas. This process involves stripping electrons from xenon atoms, creating positively charged ions. These ions are then accelerated by strong electric fields through a series of grids or electrodes, propelling them out of the engine at incredibly high velocities, sometimes exceeding 90,000 miles per hour. The efficiency of ion engines lies in their specific impulse, which is a measure of propulsion efficiency. While the thrust produced by ion engines is relatively low compared to traditional rockets, akin to the weight of a sheet of paper, their extraordinary efficiency allows them to operate continuously over long durations. This sustained thrust can gradually build up significant velocity, making ion engines ideal for deep space missions where maintaining a steady acceleration over vast distances is more beneficial than short bursts of high thrust. Several pioneering missions have demonstrated the effectiveness of ion propulsion. For instance, NASA's Dawn spacecraft utilized ion engines to travel to and orbit both the asteroid Vesta and the dwarf planet Ceres, something that would be infeasible with traditional propulsion systems due to the enormous fuel requirements. Ion engines' ability to provide gradual but continuous acceleration makes them well suited for deep space exploration, where distances between celestial bodies are immense and fuel efficiency is paramount. As we set our sights on more distant targets, such as the moons of Jupiter and Saturn, or even interstellar travel, ion propulsion could prove indispensable in our quest to explore the furthest reaches of the cosmos. The Laser Interferometer Space Antenna, commonly known as LISA, is an upcoming space mission designed to detect and study gravitational waves, ripples in space-time caused by some of the universe's most violent events, such as the merging of black holes or the collision of neutron stars. LISA will be the first dedicated space-based gravitational wave observatory, capitalizing on the absence of terrestrial limitations like seismic noise and atmospheric interference, which affect ground-based detectors like LIGO. LISA will consist of a trio of spacecraft arranged in a triangular formation, trailing behind Earth in its orbit around the Sun, with each pair of spacecraft separated by approximately 1.5 million miles. These spacecraft will use lasers to establish highly precise interferometry measurements between them. When a gravitational wave passes through this setup, it will cause minute fluctuations in the distances between the spacecraft. By analyzing these changes, scientists can infer the properties of the gravitational waves, including their sources and energies. One of the key advantages of LISA is its ability to detect lower-frequency gravitational waves that are inaccessible to ground-based observatories. These lower frequencies are generated by massive systems such as supermassive black hole mergers at the centers of galaxies or the inspiral of large compact objects. By probing these phenomena, LISA will provide insight into the most energetic processes in the universe and enhance our understanding of the fabric of space-time itself. This pioneering mission promises to open a new window into the cosmos, offering a deeper look at the gravitational side of the universe and potentially uncovering mysteries about the origins and evolution of cosmic structures. Space weather events, primarily driven by solar activity, have significant impacts on technology both on Earth and in space. These events include solar flares, coronal mass ejections, and geomagnetic storms, all of which can release vast amounts of energy and charged particles into space. When these particles interact with the Earth's magnetosphere, they can induce a range of technological disruptions. One of the most immediate effects is on satellite operations. High-energy particles can damage the delicate electronics of satellites, degrade solar panels, and interfere with communication and navigation systems. For example, geomagnetic storms can cause satellites to experience increased drag, altering their orbits and requiring adjustments to maintain proper positioning. Space weather can also disrupt the GPS systems relied upon for everything from aviation and maritime navigation to military operations. During intense solar storms, these disruptions can be severe enough to degrade the accuracy of GPS signals or even cause temporary outages. On Earth, the impacts of space weather extend to power grids and communication infrastructure. Geomagnetic storms can induce electrical currents in power lines, potentially leading to voltage instability, transformer damage, or widespread blackouts. A notable example occurred in 1989 when a powerful geomagnetic storm caused a major blackout in Quebec, affecting millions of people. Additionally, high-frequency radio communications, essential for aviation and military operations, can be disrupted by changes in the ionosphere, which reflects radio waves. As our reliance on technology grows, understanding and mitigating the effects of space weather becomes increasingly critical. Monitoring systems like the Space Weather Prediction Center help forecast these events, providing crucial warnings to protect our technological assets and maintain the resilience of our infrastructure against these cosmic phenomena. The concept of a space elevator envisions a transformative method for transporting people and materials between Earth's surface and space without the need for conventional rocket propulsion. Essentially, a space elevator would consist of a long, tethered structure extending from the surface of the Earth to geostationary orbit, approximately 22,000 miles above the equator. This tether would be anchored to a base station on the ground and balanced by a counterweight positioned in space beyond geostationary orbit. The primary component of a space elevator is the cable or tether, which must be exceptionally strong and lightweight to support its own weight and withstand the immense forces exerted throughout its length. Materials currently under consideration for this purpose include carbon nanotubes and graphene, which exhibit remarkable tensile strength and low density. Climbing vehicles or climbers, powered by electric or laser energy, would travel up and down this tether, transporting cargo and passengers in a manner similar to an elevator. Implementing a space elevator could revolutionize space access by drastically reducing the cost and complexity associated with launching payloads into orbit. Traditional rockets are expensive, fuel-intensive, and limited by their single-use nature, while a space elevator would offer a reusable, continuous, and energy-efficient means of reaching space. This would facilitate more frequent and affordable access to orbit, promoting satellite deployment, space tourism, and even the construction of space habitats. Additionally, a space elevator could serve as a critical infrastructure for transporting resources from extraterrestrial sources, such as asteroids or the Moon, thereby supporting future space-based economies. While significant technical and engineering challenges remain, the development of a space elevator holds the potential to make space exploration and utilization vastly more accessible and sustainable, ushering in a new era of human activity beyond Earth. Extremophiles are fascinating organisms on Earth that thrive in conditions once thought incapable of supporting life. These hardy life forms exist in environments with extreme temperatures, pressures, salinities, pH levels, and radiation intensities. For example, thermophiles live in the scalding waters of hydrothermal vents, while psychrophiles thrive in the icy reaches of the Arctic and Antarctic. Halophiles flourish in high salinity environments like salt flats, and acidophiles can endure the acidic conditions of sulfuric springs. These organisms have adapted unique biochemical processes to survive and reproduce in such inhospitable places. The study of extremophiles significantly influences our search for extraterrestrial life by expanding the conditions under which we believe life can exist. Traditional views often considered the habitable zone around a star where liquid water can exist to be the primary criterion for life. However, extremophiles demonstrate that life can thrive in a much wider spectrum of environments. This realization has broadened the scope of astrobiology to include potential habitats such as the subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus. These moons exhibit icy crusts with possibly liquid water beneath, influenced by tidal forces and radioactive decay. Here, extremophile-like organisms might exist, deriving energy from geothermal or chemical sources rather than sunlight. Additionally, Mars, with its history of liquid water and evidence of seasonal methane emissions, remains a prime candidate for the search for extremophile life forms. The study of extremophiles can also guide the design of scientific experiments and the development of technologies for future missions. Instruments can be calibrated to detect specific biosignatures, unique chemical indicators of life, relevant to extremophiles. Understanding how these resilient organisms operate at a molecular level helps us refine our strategies for detecting life beyond Earth, pushing the boundaries of where and how we search for extraterrestrial life. The search for biosignatures on exoplanets involves detecting specific indicators that could suggest the presence of life. Scientists employ a combination of telescopic observations, spectroscopic analysis, and theoretical modeling to identify and study these potential markers. One of the primary methods involves analyzing the light passing through the atmospheres of exoplanets as they transit their host stars. This technique, known as transit spectroscopy, enables researchers to discern the chemical composition of an exoplanet's atmosphere by examining the absorption lines in the light spectrum. Key gases that scientists look for as potential biosignatures include oxygen, ozone, methane, and nitrous oxide. On Earth, these gases are primarily produced by biological processes, so their presence on another planet could hint at life. For example, oxygen and ozone are byproducts of photosynthesis, while methane can be produced by both biological and geological processes. Detecting an imbalance among these gases, particularly those that would not be stable in the atmosphere without continuous replenishment by some internal process, could strongly suggest biological activity. Another promising approach involves direct imaging, where advanced telescopes equipped with high-contrast imaging capabilities aim to capture direct visuals of exoplanets. Instruments like the James Webb Space Telescope, set to observe exoplanets in unprecedented detail, will use coronagraphs and star shades to block out the overwhelming light of host stars, allowing the faint light from exoplanets to be analyzed. By studying this light, scientists can gather data on an exoplanet's surface conditions and atmospheric composition, further refining the search for biosignatures. Beyond atmospheric gases, scientists also consider other potential biosignatures, such as unusual surface reflectance spectra that could indicate vegetation or microbial mats, as well as temporal changes in atmospheric composition that could hint at seasonal biological activity. By combining these methods and leveraging increasingly sophisticated technologies, scientists are honing their ability to detect and interpret biosignatures, bringing us closer to answering the profound question of whether we are alone in the universe. The possibility of life in the subsurface oceans of icy moons has become an exciting area of research in astrobiology. Moons such as Jupiter's Europa and Saturn's Enceladus are prime candidates because they harbor vast oceans beneath their icy crusts. These subsurface oceans are kept in a liquid state due to tidal heating, a process where the gravitational pull of their parent planets generates internal friction and heat within the moons, preventing the water from freezing solid. Europa, for instance, has a surface covered in a thick layer of ice, beneath which lies a suspected ocean possibly containing twice as much water as all of Earth's oceans combined. The interaction between the ocean and the moon's rocky mantle could provide the chemical energy needed to support life. Hydrothermal vents on the ocean floor, similar to those found on Earth, could offer a habitat where life might thrive. These vents provide a combination of heat, minerals, and chemical energy, creating conditions that, on Earth, support rich ecosystems teeming with life. Enceladus presents another intriguing case. The Cassini spacecraft discovered plumes of water vapor and organic compounds erupting from fissures in the Moon's ice shell, indicating the presence of a subsurface ocean. The plumes contain not just water but also salts and organic molecules which are essential for life. The fact that these compounds can be detected directly from space makes Enceladus a particularly accessible target for future missions aimed at seeking signs of life. Exploring these moons for signs of life involves a variety of mission concepts. Probes could be sent to sample the plumes of Enceladus directly, analyzing the ejected materials for biosignatures. For Europa, a lander equipped with instruments designed to penetrate the ice and probe the underlying ocean could be deployed. By studying these environments and the potential habitability of their subsurface oceans, scientists hope to understand whether life can exist in such alien conditions and, in turn, gain insights into the resilience and adaptability of life in the universe. Preventing contamination when exploring potentially habitable worlds is a critical aspect of planetary protection, guided by strict international protocols and guidelines. These measures aim to avoid both forward contamination, the transfer of Earth-originating life to other celestial bodies, and backward contamination, the introduction of extraterrestrial materials to Earth, which could pose unknown risks. The Committee on Space Research sets planetary protection standards that space agencies worldwide adhere to rigorously. One key strategy to prevent contamination involves sterilizing spacecraft and instruments before launch. Techniques include heat sterilization, where components are baked at high temperatures, and chemical sterilization using potent disinfectants. Additionally, certain parts of the spacecraft, particularly those expected to come into direct contact with potentially habitable environments, may be assembled in ultra-clean facilities known as clean rooms to minimize microbial presence. Engineers wear full-body suits to avoid shedding skin particles or other contaminants. For missions targeting places like Mars, Europa, or Enceladus, where there is a higher likelihood of encountering environments hospitable to life, even more stringent measures are applied. For instance, the Mars rover Curiosity underwent thorough sterilization processes, and its design included redundancy in scientific instruments to reduce the risk of failure due to sterilization procedures. Future missions, such as potential probes to Europa or Enceladus, might incorporate similar, if not more advanced, sterilization and containment protocols. Another preventive approach involves trajectory biasing. Spacecraft that are not fully sterilized are deliberately directed to avoid accidental impact with their target celestial bodies. For example, the Galileo spacecraft, after its mission, was deliberately crashed into Jupiter to prevent any potential contamination of its moons, particularly Europa. In the event of sample return missions, strict quarantine and containment procedures will be essential. Return samples would be handled in biosafety level facilities equivalent to those used for containing highly infectious pathogens. These facilities ensure that any potential backward contamination is tightly controlled and studied under safe conditions. By meticulously implementing these methods, scientists and engineers work to ensure the integrity of both terrestrial life and extraterrestrial ecosystems. Planetary protection is paramount not just for the scientific purity of exploring other worlds, but also for preserving the potential for discovering extraterrestrial life in its true unaltered state. Dragonfly is an ambitious mission led by NASA that aims to explore Titan, Saturn's largest moon, renowned for its thick, nitrogen-rich atmosphere and surface lakes of liquid methane and ethane. Unlike any previous missions, Dragonfly will deploy a rotorcraft, akin to a large drone with 8 rotors, specifically designed to fly through the dense atmosphere of Titan. This groundbreaking approach will allow it to cover diverse terrains far more effectively than a rover could, conducting a series of hops, each up to 5 miles apart, accumulating to over 100 miles during its mission. The primary objective of Dragonfly is to probe into Titan's complex chemistry, searching for prebiotic chemical processes that might mirror the conditions that led to life on Earth. Equipped with sophisticated instruments, Dragonfly will sample and analyze the Moon's surface and atmosphere, looking for organic molecules and potential biological markers. Scientists are particularly interested in Titan's dune fields and the icy crust, where interactions between organic compounds and water can create fascinating chemistry. By examining these areas closely, Dragonfly aims to uncover chemical ingredients essential for the potential emergence of life, shedding light on what conditions might make a celestial body habitable. Scientists employ spectroscopy to detect potential signs of life on distant planets by analyzing the light emitted, absorbed, or reflected by these celestial bodies. When light interacts with matter, it can be broken down into its constituent colors or wavelengths, forming what's known as a spectrum. Each element or molecule has a unique spectral signature, much like a fingerprint, that can be identified by the specific patterns of lines or bands it produces in the spectrum. In the hunt for extraterrestrial life, scientists focus on identifying certain biomarker gases in a planet's atmosphere through spectroscopy. For example, the presence of oxygen in significant quantities can suggest photosynthetic life, while methane could indicate biological processes, particularly if found alongside gases like carbon dioxide. Advanced instruments aboard telescopes, such as those on the James Webb Space Telescope or the European Extremely Large Telescope, collect the light from distant exoplanets and pass it into spectra. By meticulously studying these spectra, scientists can discern the chemical composition of an exoplanet's atmosphere and surface, searching for these biosignatures. The interplay of detected molecules gives researchers clues about the planet's potential habitability and any possible biological activities. Phosphine has recently captured widespread scientific interest in the search for life on Venus due to its potential as a biomarker. On Earth, phosphine is predominantly produced by anaerobic microorganisms, which thrive in environments devoid of oxygen, such as in swamps, wetlands, and the guts of certain animals. Considering the extreme and acidic conditions of Venus, the detection of phosphine in its atmosphere sparked considerable excitement and speculation. In 2020, a team of astronomers reported finding traces of phosphine in the clouds of Venus at altitudes where temperatures and pressures are relatively mild. This discovery was made using spectroscopic techniques with signals indicating the presence of phosphine gas. Given Venus's harsh surface conditions, marked by scorching temperatures and crushing pressures, these cloud layers emerged as intriguing sites for potential habitability. The critical aspect of this finding is that non-biological processes known to produce phosphine, such as volcanic activity or lightning, cannot readily explain the observed quantities. If ongoing investigations confirm the presence of phosphine and rule out non-biological production methods, it may imply microbial life existing in Venus's upper cloud decks. Further exploration and research are necessary to understand the exact source and implications of phosphine on Venus fully. Missions like the proposed Veritas and Da Vinci Plus aim to gather more data about the planet's atmosphere and surface, which could either reinforce or repudiate the notion of microbial life floating in the Venusian clouds. Life on Earth has adapted to a multitude of environments, but the possibility of life evolving in radically different conditions elsewhere in the cosmos broadens the horizon of what scientists consider habitable. For instance, extremophiles, organisms robust enough to thrive in Earth's most inhospitable conditions, provide a template for understanding how life might emerge and persist under radically different circumstances. Take, for example, the hypothesis of life evolving on a planet with oceans of methane and ethane, akin to Saturn's moon Titan. Such life forms would necessitate biochemistry fundamentally distinct from Earth-based life, likely utilizing methane as a solvent instead of water. Their cellular structures and metabolic processes would need to withstand extremely cold temperatures, around 94 Kelvin, while harnessing chemical reactions unique to a hydrocarbon-rich environment. Alternatively, on a planet with high radiation levels or acidic oceans, organisms could evolve with some form of radiation-resistant biochemistry or possess cellular mechanisms that neutralize or repair high radiation-induced damage. In the extreme pressure conditions found on Jupiter's moon, Europa, or Saturn's moon Enceladus, life forms might exist in subsurface oceans beneath thick layers of ice. Here, energy sources like hydrothermal vents, similar to those found in Earth's deep oceans, could support chemosynthetic ecosystems that rely on chemical energy rather than sunlight. Endolithic organisms on Earth, which live inside rocks and derive energy from the chemicals in their environment, also inspire the idea of microbes thriving within the ice or rock layers of these moons. While the exact nature of alien life remains speculative, The diversity of life on Earth underscores life's capacity to adapt in astonishingly varied conditions, encouraging scientists to keep an open mind about potential habitable niches across the universe. The discovery of organic molecules on Mars and other celestial bodies holds immense significance for our understanding of the potentials for life beyond Earth. Organic molecules, which are compounds primarily composed of carbon atoms bound to hydrogen, oxygen, and other elements, are the foundational building blocks of life as we know it. Their presence indicates that the essential ingredients for life might be more widespread in the universe than previously thought. On Mars, missions like NASA's Curiosity rover have detected a variety of organic molecules in ancient Martian rock and soil samples. These findings suggest that Mars once had the chemical environment necessary for life to possibly develop. The significance of this discovery is further amplified when considering Mars's historical geology, which shows evidence of ancient riverbeds, lakes, and potentially vast oceans. The detection of organics provides a tantalizing clue that these past aqueous environments might have supported microbial life, and that remnants of this life could still be preserved in the Martian subsurface. Similarly, organic molecules found on moons such as Saturn's Enceladus and Jupiter's Europa, both of which show evidence of subsurface oceans, symbolize a compelling possibility for life. Plumes of water ejected from Enceladus contain complex organic compounds, hinting at the dynamic chemistry occurring beneath its icy crust. These findings imply that the subsurface oceans may have the right conditions for life, sustained by hydrothermal activity and rich chemical interactions. The broader implication of discovering organic molecules on multiple celestial bodies is that the preconditions for life may exist throughout our solar system and beyond. This provides a profound shift in our search for extraterrestrial life, suggesting that life could arise in various forms and environments, reinforcing the notion that we may not be alone in the universe. In the context of astrobiology, defining life involves a combination of biological, chemical, and physical criteria that must be flexible enough to encompass unknown forms beyond Earth, yet specific enough to be scientifically meaningful. One widely accepted definition hinges on a set of fundamental characteristics. Life is generally seen as a system capable of growth, reproduction, metabolism, and response to stimuli. Moreover, living organisms exhibit the capability for evolution through natural selection, which drives diversity and adaptation over time. At its core, life as we know it relies on a few essential components. It is carbon-based, utilizing carbon's extraordinary ability to form stable, complex molecules such as amino acids, proteins, and nucleic acids. These molecules constitute the building blocks of cellular structures and the machinery necessary for metabolism and genetic information storage and transmission. Metabolism itself includes a wide array of chemical reactions for energy transformation, enabling growth and reproduction. The genetic code, often stored in DNA or RNA, allows for the precise replication of organisms and the transmission of hereditary traits, ensuring perpetuation and variability necessary for evolution. However, astrobiology also considers the possibility of life forms that might not conform to this terrestrial template. Scientists are exploring the theoretical potential for life based on alternative biochemistries, such as silicon-based life or organisms using solvents other than water, like liquid methane on Titan. Rigidity in definition could hinder the identification of these potential life forms. Thus, astrobiology adopts a more inclusive approach, focusing on the four primary chemical elements, hydrogen, oxygen, nitrogen, and carbon, that are efficient in forming life's known biochemistry but remaining open to other complex chemistries. In practice, the search for life includes looking for biosignatures such as specific organic molecules, unusual atmospheric gases, or structures that may indicate biological activity. This broad and adaptable definition reflects an evolving understanding of life's possibilities, driven by ongoing discoveries and technological advancements in exploring environments both within our solar system and in distant exoplanets. The cosmic dark age refers to a period in the early universe, starting roughly 380,000 years after the Big Bang, and lasting for about several hundred million years, where the cosmos existed in a state of profound darkness and relative simplicity. During this epoch, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms, rendering the plasma opaque. This period is often termed the Dark Age because the universe lacked significant light sources. Stars and galaxies had not yet formed, and the ambient radiation from the Big Bang had stretched into the microwave part of the spectrum, leaving the universe dark to optical observation. The end of the cosmic Dark Age was heralded by a crucial phase known as the Epoch of Reionization. This transformative era initiated when the first generations of stars and galaxies began to form, approximately 150 to 800 million years after the Big Bang. These early stars, often called population 3 stars, were extraordinarily massive and hot, emitting intense ultraviolet radiation. This radiation was energetic enough to ionize the surrounding neutral hydrogen gas, ripping electrons away from hydrogen atoms and gradually transforming space from an opaque medium back into a transparent one. This ionization process continued as more stars and galaxies sprang into existence, creating quasars and other luminous objects that further contributed to reionizing the universe. The observational evidence of this transition comes from studying the cosmic microwave background radiation and distant quasars. Fluctuations in the cosmic microwave background provide information about the conditions of the early universe, while the absorption spectra of distant quasars reveal the ionization state of intergalactic gas at different epochs. By analyzing these data, scientists piece together a timeline showing how the universe transitioned from the Dark Age to the complex, light-filled cosmos we observe today. The culmination of the Epoch of Reionization marks the dawn of the first galaxies and stars' luminous activity, paving the way for the rich cosmic tapestry that has since evolved. Studying the very early universe through the cosmic microwave background involves analyzing the faint afterglow of the Big Bang, which provides a snapshot of the universe when it was just 380,000 years old. The CMB is a relic radiation, permeating the cosmos and carrying critical information about the conditions of the early universe. Discovered in 1965 by Arno Penzias and Robert Wilson, this microwave radiation forms a nearly uniform background, but with slight temperature fluctuations that offer profound insights into the universe's birth and evolution. Advanced space telescopes like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have been instrumental in measuring the CMB with extraordinary precision. These measurements help cosmologists in several ways. First, the tiny temperature fluctuations, known as anisotropies, reflect the density variations in the early universe. These variations eventually grew under gravity to form the large-scale structures we see today, such as galaxies and clusters of galaxies. By studying the anisotropies, scientists can infer the initial conditions that led to the formation of these structures. Moreover, the CMB provides a wealth of information about the universe's composition, including the proportions of dark matter, dark energy, and ordinary matter. The pattern of the CMB anisotropies reveals critical parameters such as the universe's rate of expansion, its geometry, and its age. For instance, the angular size of the observed anisotropies depends on the universe's curvature, making the CMB a powerful tool to test cosmological models. Another fascinating aspect is the polarization of the CMB light, which contains clues about the state of the universe immediately after the Big Bang and the subsequent inflation period. The polarization patterns, especially the so-called B modes, could potentially provide evidence for gravitational waves generated during inflation. By dissecting these different features of the CMB, cosmologists are piecing together a coherent picture of the early universe, its composition, and its dynamic evolution, thereby addressing some of the most fundamental questions about the origin and fate of the cosmos. Cosmic inflation is a theory that proposes a short but extremely rapid expansion of the universe immediately following the Big Bang, occurring within the first tiny fraction of a second, approximately 10 to the power of negative 36 to 10 to the power of negative 32 seconds after the Big Bang. Introduced by physicist Alan Guth in the early 1980s, this concept addresses several significant problems in cosmology, including the apparent uniformity of the universe and the observed lack of large-scale irregularities. During the inflationary period, the universe expanded exponentially, enlarging by a factor of at least 10 to the power of 26 in less time than it takes for light to cross a proton. This dramatic growth smoothed out any initial irregularities and microscopic quantum fluctuations, effectively stretching them to macroscopic scales. As a result, regions of the universe that were once causally connected and thus able to exchange energy and matter were spread far apart, leading to a highly homogeneous and isotropic universe on large scales. The theory of cosmic inflation explains the uniformity of the cosmic microwave background radiation across the sky. Without inflation, regions of the universe separated by over a few degrees in the sky would not have been able to communicate or equilibrate their temperatures given the finite speed of light and the universe's age. Yet, observations show that the CMB temperature is almost the same in all directions, with only minor fluctuations. Inflation reconciles this by positing that these once connected regions were pushed beyond each other's horizons during the brief inflationary epoch. Moreover, cosmic inflation lays the groundwork for understanding the formation of large-scale structures like galaxies and clusters of galaxies. The tiny quantum fluctuations that existed before inflation were magnified to scales observable today. These fluctuations served as the seeds for gravitational collapse, leading to the formation of all the complex structures seen in the universe. Overall, cosmic inflation provides a compelling framework to explain the striking uniformity of the universe, the nature of primordial density perturbations, and the large-scale structure formation, supported by a range of observational evidence and refined by ongoing research in cosmology. The formation of the first stars and galaxies, also known as cosmic dawn, marked a pivotal epoch in the history of the universe. This process began during the end of the cosmic dark age, a few 100 million years after the Big Bang, when density fluctuations in the early universe caused by quantum perturbations were amplified through gravitational collapse. These primordial density fluctuations were the seeds from which the first stars and galaxies emerged. As the universe expanded and cooled, neutral hydrogen gas started to accumulate in increasingly dense regions under the influence of gravity. These clumps of gas underwent a process of cooling further, primarily through the emission of radiation, enabling them to contract. Conditions in these regions, often referred to as dark matter halos because they are dominated by dark matter, gradually became suitable for star formation. When a clump of gas was dense and cool enough, it fragmented into smaller pockets, each of which continued to collapse under its own gravity. The first stars, designated as population 3 stars, were significantly different from the stars we observe today. These stars were composed almost entirely of hydrogen and helium, with virtually no heavier elements, also known as metals, which are synthesized in the cores of stars and distributed through supernova explosions. Due to the lack of cooling agents found in more metal-rich gas, population 3 stars were massive, hot, and short-lived, with masses ranging from tens to hundreds of times that of the Sun. Their intense ultraviolet radiation had enough energy to ionize the surrounding hydrogen gas, thereby beginning the process of reionization, which ultimately made the universe transparent to light. Following the formation of the first stars, these massive stars went supernova, dispersing heavier elements into the surrounding medium. This enrichment with heavier elements allowed subsequent generations of stars, population 2 and population 1 stars, to form under cooler and more varied conditions, facilitating the creation of rocky planets and more complex celestial structures. The first stars also emitted strong ultraviolet radiation and powerful stellar winds that influenced their surroundings, contributing to the formation of the first galaxies. Galaxies began as small proto-galactic fragments, merging over cosmic time to form the larger, more complex galaxies we see today. Through the hierarchical assembly, small galaxies merged, grew, and evolved, with processes such as star formation, supernova feedback, and the accretion of intergalactic gas shaping their evolution. Observations from powerful telescopes like the Hubble Space Telescope have captured images of these early galaxies, allowing astronomers to study their characteristics and better understand the cosmic era when the universe transitioned from darkness to a realm filled with light and structured beauty. Galaxy mergers play a critical role in the cosmic evolution, profoundly influencing galaxy formation, growth, and the overall structure of the universe. These mergers are a natural consequence of the gravitational pull that galaxies exert on each other, especially in the densely populated regions of space like galaxy clusters. Over cosmic time, galaxies frequently collide and combine, driving significant changes in their morphology, star formation rates, and galactic dynamics. During a galaxy merger, the gravitational interactions between the colliding galaxies can trigger intense bouts of star formation, known as starbursts. As the galaxy's gas clouds collide and compress, conditions become ripe for rapid star formation, leading to the creation of massive clusters of young, bright stars. This heightened activity can significantly alter the galaxy's luminosity and spectral characteristics, rendering them observable in various wavelengths, from the visible to the infrared. The infrared light, in particular, is often enhanced due to the dust heated by newly formed stars. Furthermore, galaxy mergers are instrumental in the formation of different types of galaxies observed today. For instance, the collision and subsequent merging of two spiral galaxies are thought to result in an elliptical galaxy, characterized by a more diffuse and less structured appearance. Throughout the merger process, the intricate dance of stars and gas reshapes the galactic structure, transforming the spiral arms into a smoother, more spheroidal shape typical of elliptical galaxies. These interactions also have implications for the central supermassive black holes found in most large galaxies. During a merger, the black holes from the merging galaxies can eventually coalesce, growing in mass and influencing the dynamics and evolution of the resulting galaxy. The inflow of gas towards the center during the merger can fuel the black holes, triggering active galactic nuclei phenomena, releasing vast amounts of energy and radiation that can further impact star formation and the interstellar medium. Over longer timescales, galaxy mergers contribute significantly to the hierarchical buildup of structure in the universe. Smaller galaxy mergers gradually build up larger galaxies, and this accretion process is fundamental to the growth of galaxy clusters. Observations from instruments like the Hubble Space Telescope and simulations of large-scale structure formation illustrate that the universe we observe today, with its vast diversity of galaxy morphologies and structures, is a direct result of these incessant and intricate merger processes. Thus, galaxy mergers are a linchpin in our understanding of cosmic evolution, driving the complex interplay of star formation, galactic transformation, and the growth of black holes, all of which shape the universe's grand narrative from the early post-Big Bang era to its present intricate tapestry. The rate of star formation in the universe has undergone significant changes throughout its history, reflecting the dynamic and evolving nature of cosmic structures. This evolutionary timeline can be visualized as a cosmic star formation history, which tracks the rate at which new stars have formed per unit volume over different epochs. In the earliest stages of the universe, during cosmic dawn, the star formation rate was relatively low. After the Big Bang, the universe entered a period known as the Cosmic Dark Ages, where it was predominantly dark and lacking in significant light sources. As the first stars, population 3 stars, began to form a few 100 million years after the Big Bang, the rate of star formation started to increase. These massive metal-poor stars ignited new star formation, and the subsequent supernovae enriched the interstellar medium with heavier elements, facilitating the formation of subsequent generations of stars. The star formation rate reached its zenith during a period known as the Cosmic Noon, or the peak epoch of star formation, approximately 1.5 to 3 billion years after the Big Bang. During this time, galaxies were teeming with star-forming activity, producing new stars at a rate significantly higher than today. Observations from telescopes like Hubble reveal an abundance of high redshift galaxies from this epoch, marked by intense ultraviolet and infrared emissions indicative of vigorous star formation. This peak in star formation is driven by the ample supply of cold gas within galaxies, mergers, and interactions that triggered starbursts, and the overall favorable conditions for star formation in the early universe. Following this peak, the star formation rate began a gradual decline, continuing to this day. The reasons for this decline are multifaceted, including the depletion of the interstellar gas reservoirs necessary for star formation, increased stabilization of gas within galaxies, and the feedback effects from active galactic nuclei and supernovae that heated and dispersed the gas, preventing it from collapsing to form new stars. Additionally, Cosmic expansion spreads galaxies apart, reducing the frequency of interactions and mergers that could otherwise catalyze new star formation. Currently, the universe is considered to be in a relatively quiescent phase of star formation. While stars are still forming in galaxies like our own Milky Way, the rate is much lower compared to the cosmic peak. Stellar populations are aging, and galactic dynamics now involve less dramatic transformation than those witnessed in the universe's earlier history. The cosmic star formation history offers a robust framework for understanding the processes that drive galaxy evolution and the overall cosmic narrative. By studying this history, astronomers can infer not only the formation and maturation of galaxies, but also the intricate interplay of physical processes that shape the observable universe. According to current cosmological models, the fate of the universe is largely dictated by its rate of expansion, governed by dark energy, and the amount of matter, both dark and ordinary, it contains. Current observations suggest that the universe will continue to expand indefinitely, leading to a scenario known as the Big Freeze or heat death. In this model, dark energy, identified through the accelerated expansion of the universe, plays a critical role. Discovered in the late 1990s through observations of distant supernovae, dark energy is thought to constitute about 70% of the universe's total energy density. This mysterious force works in opposition to gravity, causing the universe's expansion to accelerate over time. As galaxies move farther apart, the density of both ordinary matter and dark matter decreases, and the universe becomes increasingly dominated by dark energy. The Big Freeze scenario entails that as the universe continues to expand, galaxies will drift further apart, eventually moving beyond each other's observable horizons due to the accelerated expansion. Star formation will gradually cease as galaxies run out of the gas necessary to form new stars. Existing stars will age and die, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Over immensely long timescales, these remnants will also cool and fade away, leading to a cold, dark, and dilute universe. Another aspect of the Big Freeze involves entropy. As the universe reaches a state of maximum entropy, energy distribution will become increasingly uniform, with fewer gradients to drive processes that increase complexity. This means that over time, all physical processes, including those that could sustain life, will gradually come to a halt. An alternative but less likely scenario, depending on the properties of dark energy, is the Big Rip, where the acceleration of the expansion continues to increase, eventually tearing apart galaxies, stars, planets, and even atomic particles. If the energy density of dark energy increases over time, this catastrophic end could occur, but current evidence does not favor this outcome. Lastly, there's the Big Crunch hypothesis, which posits that the universe could eventually reverse its expansion and collapse back into a highly dense state. This scenario was considered more plausible before the discovery of accelerating expansion. However, current measurements indicate that this is unlikely given the observed dominance of dark energy. The precise fate of the universe depends on the detailed properties of dark energy, which remain one of the biggest mysteries in modern cosmology. As our understanding of dark energy and its long-term behavior improves through observations and theoretical advances, our predictions about the ultimate fate of the universe will become more refined. For now, the Big Freeze remains the most widely accepted scenario among scientists. Astronomers measure the age of the universe using several complementary methods, with the most robust estimates derived from observations of the cosmic microwave background, the expansion rate of the universe, and the ages of the oldest star clusters. Together, these methods provide a consistent picture of a universe that is approximately 13.8 billion years old. The most precise measurements come from studying the CMB, the remnant radiation from the Big Bang. Space observatories like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have mapped the CMB with high precision. The CMB provides a snapshot of the universe when it was just 380,000 years old, encoding information about its early conditions. By analyzing the temperature fluctuations and the polarization of the CMB, scientists can infer key cosmological parameters, such as the rate of expansion, Hubble constant, the density of matter and dark energy, and the geometry of the universe. These parameters feed into the lambda cold dark matter (LCDM) model, which predicts an age for the universe with remarkable accuracy. Another fundamental method involves measuring the Hubble constant, the rate at which the universe is expanding. This is done by determining the distances to far-flung galaxies and their recession velocities, primarily through observations of type Ia supernovae and redshift. By plotting these distances against their velocities, astronomers construct the Hubble diagram, which helps them to determine the rate of expansion. Once the current expansion rate is known, and combined with models of how this rate has changed over time, it allows astronomers to backtrack to the Big Bang, estimating the age of the universe. Astronomers also estimate the ages of the oldest star clusters, particularly globular clusters, which are densely packed groups of ancient stars. By studying the properties of these stars, particularly their position on the Hertzsprung-Russell diagram, a plot of stellar brightness versus temperature, scientists can estimate their ages. These estimates are based on well-understood stellar evolution models. The oldest globular clusters are found to be around 13 billion years old, providing a lower bound for the age of the universe. All these methods converge on a consistent age estimate for the universe, reinforcing our understanding of cosmological history. The alignment of different methods and observations strengthens the confidence in the current age estimate, offering a coherent picture of the universe's timeline from the Big Bang to the present day. Primordial black holes are hypothetical black holes that could have formed in the early universe shortly after the Big Bang through mechanisms other than the collapse of stars. If they exist, PBHs could provide crucial insights into the conditions of the early universe and play a role in various cosmological phenomena. Their significance spans several key areas in astrophysics and cosmology. One of the most intriguing aspects of PBHs is their potential contribution to dark matter, which comprises approximately 27% of the universe's total mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it detectable only through its gravitational effects. PBHs, being massive and non-luminous, are prime candidates for non-baryonic dark matter. If a sizable fraction of dark matter were made up of PBHs, it could explain some of the gravitational effects attributed to dark matter, such as the rotational speeds of galaxies and the motion of galaxy clusters. Another significant aspect of PBHs is their potential to seed the formation of supermassive black holes found at the centers of galaxies, billions of times the mass of the Sun. The formation and rapid growth of these colossal black holes in the early universe remain a scientific puzzle. PBHs, forming early and having a head start, might have merged and accreted matter efficiently to grow into these supermassive black holes, speeding up a process that otherwise requires longer timescales. PBHs also offer insights into the dynamics of the early universe. Their formation is believed to be linked to density fluctuations in the primordial cosmos. If the density of a particular region exceeded a critical threshold, it could collapse to form a black hole. The study of PBHs could thus provide valuable information about these early density fluctuations, probing physics at energy scales unattainable by current accelerators like the Large Hadron Collider. Furthermore, PBHs could have left observable imprints in the universe's history. Their evaporation through Hawking radiation, a theoretical process where black holes emit particles and slowly lose mass, could produce high-energy particles and photons, possibly contributing to the background radiation we observe today. This evaporation might also explain certain gamma-ray bursts or cosmic ray events that are otherwise challenging to account for. The significance of primordial black holes in the early universe lies in their potential to elucidate dark matter composition, explain the rapid formation of supermassive black holes, provide a window into the early universe's density fluctuations, and offer observable effects through their theoretical evaporation. Research into PBHs remains a vibrant and speculative field, with ongoing investigations seeking to confirm their existence and understand their role in the broader cosmic framework. The composition of the universe has undergone significant changes since the Big Bang, evolving from a state of extreme simplicity to its current complex mixture of various forms of matter and energy. Understanding this evolution provides context for how the universe has developed over 13.8 billion years. Initially, right after the Big Bang, the universe was in a hot, dense, and highly energetic state. During the first few minutes, a period known as Big Bang nucleosynthesis occurred, producing the light elements. Around 3 minutes after the Big Bang, the temperatures dropped sufficiently for protons and neutrons to combine, forming hydrogen, helium, and trace amounts of lithium and beryllium. Roughly 75% of the universe's mass was in hydrogen, about 25% in helium, and the rest in trace amounts of other light elements. This primordial composition remains relatively unchanged in regions of the universe that have not experienced significant star formation. As the universe expanded and cooled, it transitioned into a period known as the Cosmic Dark Ages, lasting until the first stars and galaxies began to form about a few 100 million years later. Without stars, the primary constituents of the universe remained hydrogen, helium, and dark matter. The formation of the first stars from these primordial gases marked the beginning of a significant transformation. These first stars, known as population 3 stars, were massive, hot, and short-lived. They initiated the process of stellar nucleosynthesis, where nuclear fusion in the cores of stars produced heavier elements, or metals in astronomical terminology, elements heavier than helium. When these stars exploded as supernovae, they expelled these heavier elements into the interstellar medium, enriching the surrounding gas. This process gradually increased the metallicity of the universe. As successive generations of stars formed and died, heavier elements continued to accumulate, contributing to the chemical diversity observed in the current universe. The formation of galaxies, driven by gravitational collapse of dark matter halos, further influenced the composition of the universe. Galaxies act as factories for star formation and element generation through ongoing cycles of stellar birth, evolution, and death. Another major component of the universe is dark matter, a mysterious substance that does not interact with electromagnetic radiation and thus does not emit, absorb, or reflect light. While it constitutes about 27% of the universe's mass energy content today, its nature remains one of cosmology's great mysteries. Dark matter primarily influences the universe's structure and formation through its gravitational effects, playing a crucial role in the formation and evolution of galaxies and large-scale structures. The most profound change in the universe's composition came with the discovery of dark energy in the late 1990s. Dark energy is a form of energy that permeates all of space and accelerates the expansion of the universe. It now constitutes roughly 68% of the universe's total energy density. Unlike dark matter, which clusters and influences the formation of cosmic structures, dark energy drives the accelerated expansion, affecting the universe's overall geometry and fate. The composition of the universe has evolved from a simple mixture of hydrogen, helium, and traces of other light elements to a complex interplay of ordinary matter, and dark energy. This evolution has driven the formation of stars, galaxies, and larger cosmic structures, shaping the universe into what we observe today. The holographic principle is a provocative theory in theoretical physics that suggests that all the information contained within a volume of space can be represented on the boundary of that space, much like a hologram. This principle emerged from the study of black hole thermodynamics and quantum mechanics, providing profound implications for our understanding of gravity and the nature of the universe itself. The concept originated in the 1990s, particularly through the work of physicists Gerard 't Hooft and Leonard Susskind. They proposed that the maximum amount of information or entropy within a given volume is proportional to the area of the boundary surrounding that volume rather than the volume itself. This means that, in a sense, the three-dimensional universe can be described by information encoded on a two-dimensional surface. One of the key motivations behind the holographic principle comes from the study of black holes. According to the work of Stephen Hawking and Jacob Bekenstein, black holes possess entropy, a measure of the amount of information about the physical state of a system. Remarkably, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This led to the insight that information within a black hole, and by extension perhaps within any region of space, could be encoded on its boundary. In string theory, the holographic principle received a powerful mathematical formulation through the AD-CFT correspondence proposed by Juan Maldacena in 1997. This conjecture posits a duality between a type of string theory defined on a higher dimensional spacetime, anti-de Sitter space, and a conformal field theory defined on its lower dimensional boundary. In practical terms, it suggests that a gravitational theory in a given volume of space can be fully described by a quantum field theory without gravity on the boundary of that space. If the holographic principle applies to our universe, it would revolutionize our understanding of space, time, and information. It implies that the physics within any region of the universe could be entirely described by data encoded on its boundary, suggesting that our perceived three-dimensional reality might be a projection from a two-dimensional surface. This could offer new approaches to resolving long-standing problems in theoretical physics, such as the reconciliation of general relativity with quantum mechanics. Furthermore, the principle has profound implications for cosmology, including the nature of the Big Bang, dark energy, and the ultimate fate of the universe. For instance, some theoretical models suggest that the observable universe could itself be a holographic projection from a boundary at infinity. Insights gleaned from the holographic principle might help physicists develop a more cohesive theory of quantum gravity, one that unites the macroscopic laws of general relativity with the microscopic principles of quantum mechanics. While the holographic principle remains a theoretical construct without direct experimental verification, it continues to offer fertile ground for research and has become a cornerstone in contemporary theoretical physics. Its profound implications challenge our conventional notions of reality, encouraging novel perspectives and mathematical frameworks to understand the universe's deepest mysteries. Parallel universe theories, particularly the many worlds interpretation of quantum mechanics, provide an intriguing framework for explaining quantum phenomena that defy classical intuition. This interpretation, proposed by physicist Hugh Everett III in 1957, attempts to make sense of the perplexing behavior of particles and the fundamental principles of quantum mechanics. In quantum mechanics, particles exist in a state of superposition where they can be in multiple states simultaneously until an observation or measurement is made. This behavior is illustrated famously by Schrödinger's cat, a thought experiment in which a cat in a sealed box is considered both alive and dead until someone opens the box to observe it. The act of measurement forces the system to collapse into one of the possible states. The traditional Copenhagen interpretation of quantum mechanics posits that this collapse occurs randomly upon measurement. However, the MWI suggests a different approach. It proposes that all possible outcomes of quantum measurements do actually occur, but in separate, parallel universes. Instead of collapsing into a single state, the universe splits into multiple, non-interacting branches, each representing a different outcome. In one universe, the cat is alive. In another, it is dead. The MWI provides a deterministic framework where the wave function of a quantum system evolves smoothly and without collapse. Every possible state of the system's wave function manifests in a branching universe, allowing for all potential outcomes to happen simultaneously but in different realities. This eliminates the need for randomness or a special role for the observer, treating all parts of the quantum system and the measurement device as quantum objects governed by the same rules. The idea of parallel universes offers compelling explanations for several quantum phenomena. Quantum entanglement, for instance, is addressed within the many worlds interpretation by proposing that when two particles become entangled, their combined wave function spans multiple universes. Each outcome reflects a different reality where the particles' measurement results are correlated across these branches. This eliminates the need for spooky action at a distance, as each universe contains its own consistent outcome. In terms of quantum superposition, the existence of multiple universes where each possible state is realized provides a natural explanation. Instead of a particle being in multiple states at once, it exists in one state per universe. Regarding quantum interference, phenomena like the double-slit experiment, where particles display wave-like interference patterns, can be understood within MWI as interactions between different branches of the universe. Each path the particle could take corresponds to a different universe, and the interference pattern arises from the coherent superposition of these paths. While the many-worlds interpretation is mathematically consistent and offers a deterministic view of quantum mechanics, it is not without its challenges. One major issue is its testability. The existence of parallel universes remains beyond the reach of empirical verification, as we cannot observe or interact with these other branches. Furthermore, MWI requires us to reimagine our understanding of reality and raises philosophical questions about the nature of existence and identity. In sum, parallel universe theories like the many worlds interpretation provide a coherent and intriguing explanation for quantum phenomena, allowing all possible outcomes of quantum events to coexist in a vast multiverse of branching realities. While it remains a topic of theoretical debate, the MWI continues to inspire discussions and research in both physics and philosophy, pushing the boundaries of how we comprehend the fundamental nature of the universe. Quantum entanglement is a fundamental phenomenon in quantum mechanics, where pairs or groups of particles become interlinked in such a way that the state of one particle cannot be described independently of the state of the others, no matter how far apart they are. This interconnection persists regardless of distance, meaning that a change in the state of one entangled particle will instantaneously affect the state of the other, seemingly violating the classical expectation that information cannot travel faster than the speed of light. The concept of entanglement was famously described in a thought experiment by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935, which is known as the EPR paradox. They pointed out that entanglement leads to what Einstein called spooky action at a distance, highlighting the tension between the non-locality of quantum mechanics and the local reality of classical physics. Quantum entanglement challenges our understanding of space and time in several profound ways. Non-locality is one such challenge. In classical physics, objects have definite positions and velocities, and interactions occur locally, either through direct contact or via fields propagating at the speed of light. Entanglement defies this locality. Once particles are entangled, measuring the state of one particle instantly determines the state of the other, regardless of their spatial separation. This instantaneous correlation implies a form of communication or connection that transcends the limitations imposed by light speed, suggesting that distance works differently in the quantum realm. Entanglement also exhibits temporal independence. Unlike classical interactions, the entangled particles' link does not diminish over time or distance. This timeless connectivity means changes in the state of one particle are instantly reflected in its entangled partners, regardless of when or where these changes are measured. This behavior suggests that our classical views of past, present, and future might need rethinking within the quantum context. Additionally, entanglement challenges classical realism, the idea that particles have well-defined properties and states independent of measurement. In an entangled state, particles do not have individual independent states. Their properties are inherently linked, and examining one particle immediately determines the state of the other. This defies the classical notion that objects possess their properties regardless of observation. John Bell's theorem and experiments further highlight these challenges. Bell formulated inequalities to test the predictions of quantum mechanics against those of local hidden variable theories, which attempt to explain entanglement using local realism. Experimental violations of Bell's inequalities provide strong evidence that quantum entanglement cannot be explained by any local hidden variable theory, reinforcing the non-classical, non-local nature of real-world entanglement. The implications of quantum entanglement are profound and far-reaching, prompting a reconsideration of the fundamental structure of the universe. It has philosophical implications for our understanding of reality and practical implications for emerging technologies like quantum computing and quantum cryptography. Quantum computers promise to leverage entanglement to solve complex problems far beyond the capacity of classical computers. Quantum cryptography uses entanglement to offer theoretically unbreakable encryption methods, as any attempt to eavesdrop on the entangled particles would disturb their state and be detectable. In sum, quantum entanglement exemplifies the deep and often perplexing connections between particles that challenge our classical understanding of space, time, and reality, suggesting that the universe operates on much more subtle, interconnected principles than those observed in our everyday macroscopic world. Loop quantum gravity is an ambitious theoretical framework that seeks to reconcile general relativity with quantum mechanics, addressing one of the most significant challenges in modern physics: the unification of these two fundamental theories into a coherent theory of quantum gravity. Unlike string theory, which posits that the fundamental constituents of the universe are one-dimensional strings, LQG takes a different approach by quantizing the very fabric of spacetime itself. At its core, general relativity describes gravitation as the curvature of spacetime caused by mass and energy. Spacetime is treated as a smooth, continuous entity. On the other hand, quantum mechanics successfully describes the behavior of particles and fields at the smallest scales, incorporating principles like superposition and entanglement. However, because quantum mechanics inherently involves probabilities and uncertainties, a direct application to the smooth spacetime of general relativity leads to significant theoretical and mathematical difficulties. Loop quantum gravity attempts to overcome these issues by proposing that spacetime is not continuous but made up of discrete quantized units. According to LQG, spacetime is composed of finite loops woven into a fine network or web known as a spin network. These loops, or spin networks, are the fundamental building blocks, and their interactions define the geometry of spacetime at the Planck scale, which is about 10 circumflex minus 35 meters. Several key aspects of loop quantum gravity include: quantization of geometry is a fundamental concept in LQG. Here, geometric properties like area and volume are quantized, meaning they exist in discrete indivisible units, similar to energy levels in an atom. Calculations predict that areas and volumes have minimum possible values, which helps to avoid the singularities and infinities seen in classical general relativity, such as those at the center of black holes or the Big Bang. LQG employs spectral analysis, a mathematical tool from quantum theory, to investigate the spectrum of geometric operators. This enables physicists to study space at microscopic levels, uncovering how space itself might behave in a quantum mechanical manner. The loop representation is another critical aspect. In LQG, the equations of general relativity are reformulated to be solved using loop variables instead of the traditional spacetime metric. These loop variables help redefine the theory at a quantum level, incorporating the probabilistic nature of quantum mechanics into the fabric of spacetime. Background independence is a remarkable feature of LQG, maintaining the principle from general relativity that the theory does not require a fixed spacetime background. Instead, the geometry of spacetime evolves dynamically within the theory itself, an essential characteristic for any quantum gravity theory aiming to unify with general relativity. In terms of time evolution, LQG conceptualizes spacetime as evolving through discrete steps. The dynamical evolution of spin networks is described using a structure called a spin foam, depicting how spin networks change over time. This approach is akin to considering spacetime as a kind of quantum foam, continuously shifting and evolving. Loop quantum gravity has facilitated new ways of looking at classical problems. For instance, LQG offers potential resolutions to the singularities present in black holes and the Big Bang. Instead of singularities, LQG predicts a bounce, where gravitational effects become repulsive at extremely high densities, possibly leading to scenarios where black holes may give way to new regions of space or even new universes. While still a developing field, loop quantum gravity represents a promising avenue for understanding the quantum nature of spacetime, bridging the gap between general relativity and quantum mechanics. As research progresses, experiments and observations may eventually provide more clues, helping to validate or refine this theoretical framework and bringing us closer to a complete understanding of the fundamental workings of the cosmos. Cosmic topology is a branch of cosmology that studies the overall shape, size, and structure of the universe on a large scale, beyond the local geometrical properties described by general relativity. While general relativity describes the curvature of spacetime due to mass and energy, cosmic topology explores how the universe might be connected, wrapped, or finite in its global structure. The shape of the universe is often discussed in terms of its geometry and topology. The geometry tells us about the local curvature of the universe, which can be flat, positively curved, or negatively curved. Observations, particularly from the cosmic microwave background measurements by missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, suggest that the universe is very close to being flat. However, this local flatness doesn't rule out more intricate global structures. Cosmic topology explores whether the universe is finite or infinite and its overall shape. For a flat universe, several topologies are possible. An infinite flat universe is the simplest idea, where the universe extends infinitely in all directions without repeating, akin to an infinite plane. A finite flat universe with identifications means that even if the universe is flat, it could still be finite if its spatial dimensions wrap onto themselves. This is similar to a torus, donut shape, in 3 dimensions. Imagine a flat surface where opposite edges are identified to form a cylinder. If the cylinder's ends are also identified, you get a torus. In higher dimensions, this construction allows for a finite universe without edges, where traveling far enough in one direction brings you back to your starting point. A positively curved universe has a spherical topology. If the universe has positive curvature, it could be closed and finite, like the surface of a sphere. Travelers moving straight in any direction on such a surface would eventually return to their starting point. The 3-dimensional analog is a 3-sphere, an extension of the spherical surface concept to higher dimensions. In a negatively curved, multi-connected universe, the global structure could involve multiple connected finite regions, creating a tessellated pattern. This hyperbolic universe might be finite yet unbounded, covered by intricate tiling patterns far more complex than those of flat or positively curved spaces. Scientists study cosmic topology using various methods. The cosmic microwave background offers a snapshot of the early universe and is vital for understanding its structure. Patterns and correlations in the CMB can reveal clues about the universe's global geometry and topology. For example, specific matching circles or repeating patterns in the CMB sky might suggest a multi-connected topology, where the same region of space is observed from different directions due to spatial wrapping. Large-scale structure and galaxy surveys examine the distribution of galaxies and galaxy clusters to uncover information about the universe's large-scale structure. Anomalies or patterns in these distributions might indicate a non-trivial topology. Cosmic rays and light paths are also studied to reveal evidence of a finite topology. By examining the paths of high-energy particles and light from distant quasars or gamma-ray bursts, scientists might find intersecting paths that indicate unusual finite topologies. Understanding cosmic topology enhances our knowledge of the universe's fundamental nature, going beyond conventional cosmological models that typically assume a simple infinite or finite global structure. Although many of these ideas remain theoretical and challenging to test empirically, advancements in observational cosmology continually offer new opportunities to explore the universe's true shape and structure. The idea that our universe might be a simulated reality, known as the simulation hypothesis, suggests that our perceived reality could be a highly advanced digital construct created by an intelligent entity, possibly a future advanced civilization. This provocative idea spans philosophy, physics, and computer science, with several arguments and theories proposing how and why we could be living in a simulation. Philosopher Nick Bostrom, in his influential paper, "Are You Living in a Computer Simulation?", proposed a formal framework for the idea based on probabilistic reasoning. Bostrom's argument involves 3 core propositions. Technological capability implies that any sufficiently advanced civilization could develop immense computing power to simulate entire universes with incredible detail and accuracy, including the consciousness of beings within that simulation. Ancestor simulations suggest that such advanced civilizations might create simulations of their ancestors or past historical events for research, entertainment, or other purposes. Statistical probability indicates that if many such simulations exist, the number of simulated realities would vastly outnumber the single base reality. Therefore, the probability of any observer being in one of these many simulations is much higher than being in the original base reality. Proponents of the simulation hypothesis often draw analogies to advancements in our technology. Video games, virtual reality, and computational simulations of physical processes have become increasingly sophisticated, suggesting a trajectory where future technological progress could enable the creation of simulations indistinguishable from real reality. Key aspects and arguments supporting the simulation hypothesis include: digital physics suggests that the universe exhibits properties akin to sophisticated computation. The quantized nature of space and time and the discrete energy levels in quantum mechanics could resemble digital processes underlying a simulated environment. Fine-tuning of physical constants, which allows for complex structures like galaxies, stars, planets, and life itself, seems improbably precise. The simulation hypothesis offers an explanation that these constants were deliberately set by the creators of the simulation to achieve specific outcomes. Information-theoretic evidence shows that theoretical physics increasingly incorporates concepts of information and computation. Ideas from quantum gravity and the holographic principle suggest that the fundamental nature of reality might be informational, aligning with the notion of it being a simulated construct. Unexplained phenomena and anomalies, such as unexpected particle behaviors or unresolved paradoxes, could be interpreted as glitches or artifacts of a simulation, hinting at underlying computational processes. Critics of the simulation hypothesis argue against its empirical unfalsifiability. Since the hypothesis posits that the simulation is perfect or near perfect, any evidence we might collect could itself be part of the simulation. This circular logic makes the hypothesis difficult to disprove using scientific methods. Additionally, some argue that Bostrom's probabilistic approach is based on assumptions that may not hold true, such as the motivations and capabilities of future civilizations. Despite the challenges of proving or disproving the simulation hypothesis, it continues to inspire thought-provoking discussions and research across multiple disciplines, encouraging deep reflections on the nature of reality, consciousness, and the future of technology. Whether we live in a base reality or a simulated one, exploring these ideas pushes the boundaries of our understanding and presents new perspectives on the universe and our place within it. The cosmic censorship hypothesis, proposed by Roger Penrose in 1969, addresses the nature of singularities produced by gravitational collapse and their potential visibility. Singularities are regions where the curvature of space-time becomes infinite and the laws of physics as we know them cease to apply. There are two primary forms of the cosmic censorship hypothesis: the weak and strong cosmic censorship hypotheses. The weak cosmic censorship hypothesis asserts that singularities arising from gravitational collapse are hidden within event horizons, the surfaces of black holes. This means these singularities are censored from distant observers, ensuring that the external universe remains predictable and governed by the known laws of classical physics, as information about the singularity cannot influence regions outside the event horizon. The strong cosmic censorship hypothesis posits that the deterministic nature of general relativity remains intact, even in the collapse process. It states that the laws of physics should uniquely predict the future given an initial distribution of matter and energy, implying that singularities cannot affect the predictability of the universe as a whole. The cosmic censorship hypothesis is important for several reasons. First, it preserves the predictability of general relativity, where the future evolution of space-time is determined by its initial conditions. If naked singularities, those not hidden by event horizons, were to exist, they would lead to regions where the predictability of physical laws breaks down, resulting in a loss of determinism. The weak cosmic censorship hypothesis helps preserve this predictability by ensuring that singularities, if they form, are always hidden within black holes. Second, it maintains the mathematical consistency of general relativity. If singularities could be exposed to the rest of the universe, standard physical theories might not apply, resulting in undefined or infinite quantities that cannot be reconciled with known physics. The hypothesis provides a safeguard that helps keep the theory logically coherent. Third, in astrophysical scenarios, the hypothesis guides the formation of black holes from collapsing massive stars and the evolution of such objects. Observations of black holes and their properties are consistent with the hypothesis, thereby supporting its validity. The hypothesis underpins much of our understanding of the life cycle of stars, the formation of galaxies, and the behavior of matter in extreme gravitational fields. Fourth, the study of cosmic censorship intersects with the quest for a theory of quantum gravity, aiming to unify general relativity with quantum mechanics. Understanding whether singularities are hidden or visible might provide crucial insights into the nature of spacetime at extremely small scales and high energies, where quantum gravitational effects cannot be ignored. The hypothesis offers a framework within which these more advanced theories can be developed and tested. Fifth, in cosmology, the hypothesis affects models of the universe's evolution, its initial conditions, and the ultimate fate of cosmic structures. The nature of singularities ties into broader questions about the Big Bang, cosmic inflation, and the dynamics of spacetime. While the cosmic censorship hypothesis remains unproven, it continues to be a fundamental pillar in understanding black holes and singularities within general relativity. Ongoing research seeks either to prove or to provide counterexamples to the hypothesis, refining our understanding of the universe's most extreme phenomena. The theory of eternal inflation extends the concept of cosmic inflation, suggesting that our observable universe is just one of many bubble universes within a larger multiverse. Proposed by physicist Alan Guth and later expanded by Andre Linde and others in the 1980s, eternal inflation builds on the idea of inflationary cosmology, where the early universe underwent rapid exponential expansion after the Big Bang. Here's how eternal inflation leads to the concept of a multiverse. In the inflationary model, a scalar field known as the inflaton field drives the rapid expansion. This field's potential energy landscape dictates the behavior of inflation. In many models, the potential is nearly flat, causing the field to roll slowly, which in turn causes the universe to expand exponentially. During this inflationary period, quantum mechanical fluctuations influence the inflaton field, causing different regions of space to experience varying rates of inflation. Some regions might inflate faster than others, even as inflation slows down or ends in other regions. Due to these quantum fluctuations, certain regions of space undergo continual exponential expansion, never settling into a stable state where inflation ends. These expanding regions can spawn bubbles where inflation stops, and a more typical, slowly expanding universe like our own can form. This self-reproducing nature makes inflation eternal on large scales. Each of these universes created via eternal inflation can have different physical properties depending on the conditions under which inflation ceased. These differences could include variations in fundamental physical constants, different types of particle content, or distinct laws of physics. This framework provides a natural mechanism for creating a vast ensemble of universes, each potentially unique. Eternal inflation implies an infinite number of bubble universes, each with potentially different physical laws and constants. This diversity could explain the fine-tuning of our universe's parameters, suggesting that we inhabit a universe where conditions happen to be right for life because such universes are among the vast number of possible ones. The anthropic principle, which states that the universe's laws and constants are as they are because they allow for the existence of observers like us, gains a framework within the context of a multiverse. If infinite bubble universes exist, some will inevitably have the conditions necessary for life, making our universe's seemingly fine-tuned properties less surprising. Testing eternal inflation directly is challenging because the other bubble universes would be causally disconnected from ours. However, some cosmologists speculate that traces of collisions between our bubble and others might be imprinted in the cosmic microwave background or in large-scale structures. Detecting such signatures could provide indirect evidence for the multiverse. The existence of a multiverse has profound implications for fundamental physics. It challenges the notion of a single, unique set of physical laws governing everything, and suggests that our understanding of physics might be a local phenomenon. Fundamental constants and laws could be contingent upon the particular configuration of our universe within the multiverse. Eternal inflation transforms the inflationary paradigm from a mechanism explaining the early universe's rapid expansion into a grander vision of an ever-expanding, infinitely diverse multiverse. While direct evidence remains elusive, the theory provides intriguing explanations for some of the most puzzling aspects of our universe, inspiring deep theoretical and philosophical exploration. Quantum foam, also known as spacetime foam, describes the fluctuating and turbulent nature of spacetime at the smallest scales. Proposed by physicist John Wheeler in the 1950s, it suggests that at the Planck scale, approximately 10^-35 to 10^35 meters, spacetime is not smooth and continuous, but exhibits a frothy, foamy structure due to quantum mechanical effects. The idea of quantum foam arises from the principles of quantum mechanics and general relativity. According to the Heisenberg uncertainty principle, there is a fundamental limit to the precision with which certain pairs of properties, such as position and momentum or energy and time, can be known simultaneously. At the Planck scale, this principle implies significant fluctuations in energy and spacetime geometry, leading to a frothy structure. At very small scales, spacetime is thought to be dominated by quantum effects, where geometric properties such as distance and time intervals become indeterminate. This leads to a picture where spacetime is teeming with temporary distortions, creating what Wheeler described as quantum foam. These fluctuations could manifest as rapidly appearing and disappearing micro-black holes, mini-wormholes, and other exotic topological features. In general relativity, spacetime is modeled as a smooth, continuous fabric that can be curved by the presence of mass and energy. However, when quantum effects are taken into account, this smooth model breaks down at extremely small scales. Quantum foam represents a more dynamic and stochastic structure of spacetime at these scales, suggesting that the classical notion of a smooth spacetime fabric is only an approximation that holds at macroscopic scales and higher energies. The concept of quantum foam is central to theories of quantum gravity, which aim to unify general relativity and quantum mechanics. Various approaches, such as loop quantum gravity and string theory, seek to describe how spacetime behaves at the Planck scale. In LQG, for example, spacetime is quantized, consisting of discrete loops or spin networks, which align with the idea of a foamy granular structure. Quantum foam suggests that spacetime is fundamentally different from the smooth continuum described by general relativity. It implies that at the most basic level, the universe is composed of constantly fluctuating regions of space and time, leading to a granular, foamy structure. Stephen Hawking's theoretical work on black hole radiation is closely linked to the concept of quantum foam. Hawking proposed that virtual particle pairs appear near the event horizon of a black hole due to quantum fluctuations. One particle falls into the black hole while the other escapes, leading to what is now known as Hawking radiation. This work reinforced the idea that quantum effects are crucial in understanding black hole behavior and the nature of spacetime. Quantum foam may help explain why certain fundamental constants of nature have the values they do. The complex structure of spacetime at small scales could influence the properties of particles and forces, leading to the observed constants in our macroscopic universe. Quantum foam is also related to the concept of vacuum energy, referring to the underlying energy present in empty space due to quantum fluctuations. This vacuum energy has implications for the cosmological constant and dark energy, influencing the large-scale structure and expansion of the universe. While quantum foam remains a theoretical construct, it provides a fascinating glimpse into the potential underpinnings of spacetime and the universe. As research in quantum gravity progresses, our understanding of quantum foam and its role in the fabric of spacetime may offer profound insights into the fundamental nature of reality. The idea that time might be an emergent property rather than a fundamental aspect of reality challenges the traditional view that time is a fundamental backdrop against which events unfold. Instead, it suggests that time could arise from more fundamental, timeless laws and structures. Several theories support this idea. The thermodynamic arrow of time, which emerges from the second law of thermodynamics, proposes that in a closed system, entropy tends to increase over time. From this viewpoint, time's direction is a macroscopic consequence of increasing entropy. This implies that time at a fundamental level does not necessarily flow, but that the progression of events and the growth of entropy create the sensation of a forward-moving time. In some interpretations of quantum mechanics, time may emerge from the quantum correlations between entangled particles. Carlo Rovelli's relational quantum mechanics, for example, suggests that time is a measure of the change in relationships between quantum systems. Instead of being a universal parameter, Time is viewed from the perspective of individual interactions, emerging from the complex web of relationships among quantum states. The holographic principle and its implementation in the ADS-CFT correspondence provide a framework in string theory where time could be emergent. In this correspondence, a higher dimensional gravitational theory in an anti-de Sitter space is equivalent to a lower dimensional quantum field theory on the boundary of this space-time. In this duality, the time dimension in the higher dimensional theory can emerge from the quantum entanglements and interactions in the lower dimensional boundary theory. In loop quantum gravity, space-time is quantized and composed of discrete quanta called spin networks, which describe the geometry of space at the Planck scale. Time in LQG doesn't exist independently. It emerges from the evolution of these spin networks. The theory posits that the fabric of space-time grows out of these fundamental quantum geometries, with time being an emergent aspect of the relationships and transitions between different quantum states of the spin network. Causal set theory proposes that space-time is built from discrete events ordered by causality. In this theory, space-time is a collection of discrete points with a causal order, but without any predefined geometry. The perceived continuum of space and time emerges from the large-scale structure of these causal sets, implying that time, like space, emerges from a more fundamental structure of sequential events. Some theories suggest that the fundamental laws of physics could be formulated without any reference to time. Julian Barber's shape dynamics, for example, describes the universe purely in terms of the geometrical relationships between configurations of matter, where time is seen as an emergent construct arising from the sequence of changes in these configurations. Barber's concept of time capsules posits that moments we observe as temporal succession are really configurations where all necessary data of a past state are encapsulated. The notion of time as an emergent property proposes a radical rethinking of our understanding of the universe and aligns with ongoing attempts to unify general relativity and quantum mechanics. These theories open new avenues for exploring the fundamental nature of reality, suggesting that our perception of time as a constant flowing entity might arise from deeper, more abstract principles governing the cosmos. While these ideas are still largely theoretical and require further development and experimental verification, they represent exciting frontiers in our quest to comprehend the universe's true nature.